Second. Yes. That would be the directing. Thank you. Yeah, this is fine. Yeah.
So, good afternoon, everybody. I am Aditya. I'm fourth year math UG, and I'm going to be talking about my VSRP project. My advisor was Dr. Shubhajit Goswami from AIFR Mumbai. And today we are going to take a look at random graphs. This is a very basic introduction to the field, along with some tools, along with some analytical tools in the context of a modern research problem. So, first of all, what is a random graph? I'm sure you've heard of this name, Erdos-Renyi random graph. I mean, what is it? It's basically the most typical example of a random graph that you'll see in every book. Whenever people ask you about random graphs, you'll see this name. There are other random graphs, but this is one of the most common and important. So, Erdos-Renyi random graph, it's denoted GNP. So, you basically take n vertices. Suppose you take 10 vertices, n is 10. And then between any two pair of vertices, for example, there are 45 pair of vertices and there are 10 vertices, right? For each of them, you flip a coin with heads probability P independently. If it comes up heads, then you put down an edge. If it comes up tails, you don't put down an edge. Then you flip a coin, same type of coin, independently 45 times, if n is equal to 10. So, this is like a very simple description of Erdos-Renyi random graph. Are there any questions about this? I hope everybody understood this. This is very important going forward. And first of all, we need to talk about what kind of results we can get for Erdos-Renyi random graph. I mean, suppose you have GNP, G10 comma half. What kind of results can you get? Can you say there will be an edge? You cannot, right? Every time the coin could have come up tails. But you can say that the probability of there not being an edge is very low. I mean, if n is large, then you can say that with very high probability there will be an edge. So that's sort of what we are going to keep in our minds as we go forward, because this is a random model. We cannot say anything for sure. Almost certainty is the best we can do in this case. I mean, you cannot expect more from a probability talk, but so, I mean, to talk about prerequisites, I mean, it's a good time to talk about sort of prerequisites for this. I mean, as long as you don't scratch your head when I say random variable and expectation, you should be fine. So, first of all, why care about random graphs? You don't even get certainty results, right? So, a very good example of this is sometimes a graph problem may not be easy to solve quickly in every case. But, you know, if you throw out some pathological cases, you can solve it quickly using an algorithm. For example, you know, whether or not there exists a Hamiltonian cycle in the graph, it's known to be NP complete. What is a Hamiltonian cycle? It's just a cycle in the graph that visits each vertex for one space. You don't need to know exactly what it is, just that we don't have polynomial time algorithms to solve it. And we want polynomial time algorithms. Otherwise, the problem becomes intractable in practice. But if you assume that your graph is coming from a sample of GNP, and there is a critical value of PL that will give you the answer directly. So if P is much bigger than PL, much bigger here, you don't have to worry too much about it, but it basically means small omega of PL. Then it will exist with high probability. What does it mean? The probability of such a thing happening will go to 1 as n tends to infinity. That's what it means. Again, the probability GNP will have an edge. It will have an edge with high probability. It's the same thing here. And then if P is small O of PL, it's much smaller than PL, then it will not exist. Like, it's unlikely to exist. It will exist with low probability. Probability going to 0 as n tends to infinity. So we already have an answer. Great. I mean, you have a graph. Assuming it comes from GNP, you can, obviously average out the number of edges by the number of total possible edges, and that will give you an approximate value for P. You can compare it with this threshold. You already have an answer that works very well. But then, well, maybe you say, I don't believe you. Prove it. So how do I go about finding a Hamiltonian cycle in this case? So there actually is a polynomial time algorithm that succeeds with the same probability there is a Hamiltonian cycle. So suppose you're in the Hamiltonian cycle if it isn't one, but the chances of failure are very small. So that's what that's a basic idea. It's very powerful. This is a very intractable problem, but in practice, you can end around this, and things will work out. This is one case, but there are other areas of application also in medical imaging, political science, also in epidemiology. I did not write it down because I was not clear exactly how it's applied, but it's certainly used in epidemiology. It's used in missing data editing prediction. It's used in wireless network modeling. It's also used in economics and I've been told also management. So let's talk about a key research problem that I have promised in the beginning of this talk. So what is the motivation behind this key research problem? Suppose a real life network of friends can be modeled as GNP. So two people are friends with a probability P independently of everything else. Is it a terrible model? Probably not. Is it a great model? I mean, it does not take into account the fact that some people are more social, some people, it doesn't take into account mutual friendships and everything. So if A knows B and B knows C, then A is more likely to know C. But it's not a terrible model. It has been shown to be a very good model in practice. So suppose there are two social networking sites, Facebook and Facebook. So if two people know each other in real life, suppose there is a probability S that they are friends on a given social networking website. Suppose me and this person, imaginary person standing here, are friends. Then we will be friends on Facebook with probability S and on Facebook with probability S. And Facebook and Facebook friendship have nothing to do with each other. And one friendship and another friendship have nothing to do with each other. All of this is independent. So we are Facebook and we know the screen names and we know the real names. But Facebook, we only know their screen names. How do we figure out the real names? Maybe we want to develop a business strategy. So how do we figure out what the real name of people is on Facebook? So we can figure out tendencies and everything. So, and this is a problem. Maybe this looks a little artificial, but it does have real applications. Exactly this is called noisy graph matching. You want to match two graphs where there is some noise S. So let's just look at the picture here. So this is real life. You have some network of friends, right? And we are Facebook, so we know their names. And Facebook, we only know John and James. We don't know the other people. Like other three dots could be Ava, Mary, and Bob in any of the 6 possible combinations. So this is a social network in real life. With probability S, we retained some edges. With probability 1 minus S, we deleted the other edges basically. And now we know John and James are there, but we don't know who is that dot there. We don't know that it actually is Bob. We are Facebook. We were not given access to this real life social network. We only have this graph and that graph. So how do we figure it out? I mean, let's just try a hands-on approach. Okay, so your blue is John, orange is James, and in that Facebook graph, you see one person is connected to John. Yeah?
We are giving the usernames the same.
No, the usernames are different, right? People have different usernames. We want to, otherwise the problem would be trivial, right? We just associate it with real usernames.
No, but like usernames are same across these two websites, not same as their real life.
No, real life, people have real life names, that's constant. But people can use different screen names on Facebook and Facebook.
So how does Facebook know that these two are John and James on the Facebook?
Yeah, that's a good point, right? We know, maybe because they by chance use the same screen name. Some people will use the same screen name for both websites. Maybe that they've done some external investigation. Right, so you don't need that many, you don't need 40% of them. You need very small fraction, but for illustration I've done 40%. Are there any questions? So let's try hands-on approach. I mean, blue is John, orange is James. In the Facebook graph, you see that vertex being connected to John but not James. So you would guess that's Eva, right? Connected to John but not James. Okay, Eva is connected to Bob. Eva is not connected to anybody. So, I mean, who is that first dot and who is that third dot? You cannot identify Bob and Mary properly. You're given insufficient information in some sense. We're trying our best, but it's not working. So, of course, this is a artificial example, which is why it's not working. But the idea is, can we find an algorithm that as the sample size goes to infinity, that our algorithm will work in polynomial time correctly? So the key result by Elsan Mursal and Jiazin Zhu in 2018, so this is relatively recent, there exists an algorithm which de-anonymizes the base of accounts in polynomial time, which works with high probability. I've already explained what high probability is. Under the sparse regime, and some additional assumptions on n, p and s. What is sparse regime? It basically means there are not too many edges, so p is below a certain value. There are some conditions on n, p and s so that the math works out, that you, as you will see later. I'll not discuss what exactly those are. It's an easy paper to look up, but the main idea here is we have a polynomial time algorithm. That's so let's look at our algorithm. But before that, we need a piece of notation, TML tree. So this is a T34 tree. You see that thing right there is called the root. These are called the leaves, right? And TML means T34 means arms of length 3 and 4 arms of them, and they are disjoint except at the root vertex. So it basically looks like this. It's not a binary tree. It's just a tree. I mean, so binary tree you would have two children of each vertex, right? So what is the algorithm? By the way, seeds. By seeds I mean John and James, the ones that we know in the other graph. They are called seeds. Suppose you have you in your known Facebook graph. Suppose you pick a vertex u, then you want to associate it with its Facebook account. You know, okay, this is Eva. What is her Facebook account? Okay, so find a TML rooted at u. What is M and L? It's just some parameter that you have chosen optimally. So you find a tree rooted at u, and then look at its leaves should be seeded. Whether such a tree exists, we'll discuss later. But suppose a tree exists, then you find a corresponding TML tree with the same set of leaves. Then that corresponding root will be corresponding to u. So it's basically root to root correspondence via the seeded leaves. So there are questions about correctness. Right? Does such a tree exist in Facebook and Facebook? And is the root of such a tree unique in Facebook? Otherwise, we cause problems, right? We might have misidentification. And again, we can only say these things with high probability, even if they are true, not with certainty. So whatever vertex is isolated, I mean, if you have a bunch of dots, you cannot connect them in any way using graph structure to another bunch of dots, right? You don't want isolated vertices. These are some questions that you might have about the correctness of the algorithm. So the point of my discussing this is how you develop an algorithm. You're trying to prove correctness. You think about, okay, how things might work out, like what might be problems, and then you try to prove that those problems will only happen with low probability. That's the basic idea of the proof. So the key algorithm behind key idea is the branching process structure. This will clarify a lot of things. I'll not go into the exact details of the full proof. I'll just talk about some small excerpts from it. So the graph of both Facebook and Facebook will be branching processes with upper and lower limits of growth. So what is a branching process first of all? So this is a branching process. Rate of growth is the average number of children basically. Or the number of children, not the average number of children, but the number of children. So for example, here you can see the rate of growth is like 4, 3 or 2, whatever, 3 maybe you can say. This person has a rate of, like, first generation has 4 children, second generation the first guy has 4 children, and so on and so forth. So this branching process structure, we don't want it to grow too fast, because then there will be interconnections in the graph will be too dense. We want to work under the sparse regime. Like we don't want the graph to be too dense, because then uniqueness will be in question. If you have the complete graph, then for example every edge is there, then you can find many such trees. You want there to be uniqueness. So you don't want the branching process to grow too fast, because then there will be interconnections in the graph. But also you don't want to be too slow, right? You do want to find TMLs. So how would you find TMLs centered at, say, this vertex? Well, you can just go down m generations, and then you can find these, and you can look at its nth children, and then you can find which of those are seeded. Right? Some of them will be seeded, right? Is our assumption. So that's how you would find such a TML tree. But again, this branching process structure, I'll not go too much in depth, but I just told you, okay, we need to find an upper bound on the rate of growth and a lower bound, of course. So let's worry about the upper bound. Okay, I'll not prove the lower bound, but I'm just trying to give you some idea of the tools that I use. So we are going to use the Markov inequality, which I'm sure you have heard of if you have taken a probability course. If x is a non-negative random variable, then probability is greater than equal to a for some positive a is less than equal to expectation x by a. So if x is integer valued in particular, if it doesn't take on fractional values, then probability x is greater than equal to 1, use a is equal to 1, but you can see it's equal to probability x greater than 0 because it doesn't take on any value between 0 and 1. Then it's less than equal to expectation of x. So if expectation x goes to 0 as n goes to infinity, then probability that x is greater than 0 also goes to 0. Right? You can see it from Markov's inequality. Is it clear? So, to prove the upper bound, we are going to prove that the upper bound on the maximum degree is 4 times the average degree np. So, average degree is np and the upper bound is 4 times that. So, how do we prove such a thing? So, let x be the number of vertices that have degree greater than 4 np. So, x is x1 plus up to xn, where xi is the indicator random variable of the event that highest vertex has degree that exceeds 4 np. I mean, it's very simple calculation. You're basically counting vertex by vertex whether or not it's true, and you're adding 1 to the tally if it has degree greater. So this is actually the number of vertices that have degree greater than 4 np. So expectation of x is by linearity of expectation this, and of course by vertex 1 and vertex 3 should not be different, right? So expectation x1 should be expectation x3. So you get n times expectation x1, which is n times probability that a binomial of n minus 1 comma p is greater than 4 np. Now, the latter quantity can be estimated using binomial tail bounds. There are bounds and under certain conditions on P we can show that it does go to 0. Again, exact conditions and what exact algebra you're doing for the tail bound, it doesn't matter. What matters is that you understand that binomial, if you show the expectation going to 0, then probability x is greater than 0 goes to 0. Which means that probability there exists a vertex that exceeds degree 4 np goes to 0. Which is what we wanted to show. With high probability, the maximum degree will be less than 4 np. Right? There's a bit of thinking involved, but it's nothing more convoluted than maximum degree is 4 np is the same event as x is equal to 0. No, nothing exceeds that number. So now we're going to talk about second moment method. This is amazing coupled with this first moment method. If you take a probability theory class, you'll probably see this directly, but for those of you who are not going to do that, Cayley-Zeeman inequality, suppose x is non-negative and has finite second moment, then probability that x is positive, that was a lower bound, upper bound, right? It was less than equal to. Here you have a lower bound, greater than equal to expectation x whole square by expectation x square. So if x is integer value, then the same old third point goes. And if you can show the RHS goes to 1 and then tends to infinity, then we can say x is greater than equal to 1 with high probability. Now we want it to go to 1, not 0. So let's talk about the number of isolated vertices in GMP. So again, same logic. How many isolated vertices will be there? Let xi be the indicator ix vertex is isolated. Then let x1 to let x be the number of isolated vertices. Expectation x, well, what is the probability a vertex is isolated? 1 minus p to the n minus 1. So expectation of x is that. And expectation x square, I mean, you expand x square and then you use linearity of expectation. Because x is an indicator random variable, it takes only one value 0 and 1. X square is basically x, xi square is x. So you can write it as like expectation xi square is this, probability that xi is 1, and then expectation xi and xj are both. This is the indicator that xi and xj, like I and j are both isolated. So well, I should not have a vertex and j should I should not have an edge to anything, and given that j should also not have an edge to anything else. Also, this is very simple calculation. So expectation x square you can write in this manner. So we can compute the key quantity that we saw in the previous slide. So this is, I'm going to now demonstrate the power of second moment method coupled with the first moment method. So you have this quantity. I've used some estimation. Like 1 minus p to the n minus 1 is like e to the n minus np and so on. Simple estimations. Now I define that quantity to be alpha n. So probability there is an isolated vertex is greater than equal to alpha n. For example, if p is 1 by n, then you look at this equation. P is 1 by n, then you get like e plus 1 in the denominator, in the limit, right? So alpha n is this. If p is 2 by n, 2 by n, then you will get 1 by 1 plus e square. If p is 3 by n, you will get 1 by 1 plus e cube, right? So this is like, it gives you a lower bound on the probability that there will exist an isolated vertex. So p is like k by n, then there will exist, there is actually a good probability that it will exist. It's not going to 0. So p is equal to to 1 by n is like a very small value of p, so it will leave isolated vertices. So you don't want to work in this regime. It's a very powerful. By the way, suppose we try to do the same thing using first moment, and then probability x is greater than 0 is less than equal to expectation of x, which is here, which will basically, if it's 1 by p is 1 by n, it will basically become this, and does not give you anything. Probability less than infinity, not very deep statement. So that is the thing, and finish with one last thing. You can claim p is equal to 1 by n. You can say, okay, p is equal to 1 by n is too large for it. There are too many isolated vertices. It's too small. Make p is equal to 1 by square root n. Okay. So here you see, okay, you have e to the square root n, and this will anyways go to 0. That doesn't matter. Sorry, go to 1. That doesn't matter. So you have e to the square root n. That will actually take this entire term to 0. So probability of there being an isolated edge will go to 0, which is not like it's lower bounded by 0, which is not a deep statement. If you reduce it, then you cannot show that there will exist isolated vertices. On the other hand, if you make p is equal to 1 by n square, you make it smaller, you increase the power of n, you make it smaller, then this will become like e to the 1 by n, and that will basically take this whole term to 1. That means if p is 1 by n square or k by n square, then this alpha n will go to 1, which means there will surely exist, like with high probability there will exist an isolated vertex. So we just did some arbitrary estimations. We just played around with second moments and first moments, and we got like a threshold. This is called a threshold. Below 1 by n, even for 1 by n to the 1 minus epsilon, you will get you will get something like there will be no isolated vertex, and for p equal to 1 by n 1 plus epsilon, you will actually get that there will certainly be at least one isolated vertex. This 1 by n is called threshold value. It's actually a threshold. It's not a sharp threshold, but it is a threshold. Sharp threshold we don't want. So basically the idea, you remember Pn in this slide.
Your overtime.
Yeah. So this is called a threshold. So below the threshold, property will not exist. Above the threshold, property will exist with high and low and high probability basically. So thank you very much. Are there any questions?
You're in the frame. I'm just explaining how to figure out whether there is an isolated vertex. And again, as I explained, not. Maybe if there are a bunch of dots, you cannot connect them, right? Cross class. You don't want there to be isolated vertices. Yeah, exactly. You don't have enough information. It's just one exercise which is reasonably relevant to our algorithm. It's not like mathematical. There is just one number which is display of two or three. But generally, what you see here is right. You can say that so generally, it's like either it's at an extreme or it is like at a it has a distribution.
Hello, Fluffy. I'm from page. Today I'll
what are modular forms? So, modular form, first of all, we will look into something related called modular function. The modular function of weight A is a meromorphic function on the upper half plane. Together with infinity that satisfies some transformation relations, which you can see up here. For all the integer matrices, divided integer matrices, whose determinant is 1, it follows this particular property. For weight K, we have this AZ plus B over CZ plus B is this thing. So the function is called modular form. If that meromorphic condition is replaced by holomorphic, that means it has good properties everywhere, even at infinity. Then so random. You could have played with other functional equations and maybe expect something non-trivial. But it turns out that it is very special. It has non-trivial properties which you won't expect from any random function. So let's look at the most simple case, equal to 0. Where is 0 modular form or modular function? So you have this transformation property for all A, B, C, D, integer matrices. Let's see what it is. Example. Constants. Let's give an example. It's not interesting. So, what is so interesting about them? Well, the first non-trivial, like simplest possible non-trivial example looks like this. It's a mess. It's called a J invariant, and you can see there are a bunch of terms. There is a big summation, there is a big product, and the product is raised to the power of 24. All sorts of messes going on. The sum is raised to the power of 3, and we have this number theory function, some sigma t f for n, which is the sums, the cubes of the integers from the t from the n. So all of this is defined in the upper half plane, and you can meromorphically extend it to the meromorphically extend it to infinity, wherein it has a pole. So there you go. What's so interesting about them? Well, it has a Fourier expansion. Of course, if you expand, if you consider each of these terms to be q to the power 2 pi I tau, if you replace it with q, then you can have a q series, like then just do some manipulations, algebraic manipulations, you get some q series, and it looks like this. With big integer coefficients for each possible powers of q, and it looks terrible. But I have highlighted one particular coefficient, 19684. Okay, it's if somebody knows a lot of group theory, then you will be familiar with this number, because for the largest simple group, which of size is about 10 elements, about 10 to the power 54 of them, an irreducible representation in 19683 dimensions. So it's very close to 19684. So to say something about what is meant by sporadic simple groups, so in the 20th century, mathematicians undertook a huge program of classifying finite simple groups, and they did this business throughout the century and found 26 non-trivial examples, but from many infinite families, and monster group is the largest among them. It has many other irreducible representations, but it's the smallest irreducible representation, and it acts on this very high dimensional complex vector space. And the higher coefficients are also interesting in the sense that similar relations, analogous relation holds up there as well, and these relations are grouped together in a set of conjectures together known as the 1/6 moonshine, which was explained by Richard Borcherds, and which algebra fields made. So, next. numbers, pi, which is square, and play around them, you will never expect to have such coincidences. It is like 12 nines over there. It's too close to an integer. It's like randomly playing around with something, and you find a needle in a haystack. You don't expect to find needle in a haystack, basically. It's something very weird. So what's going on? So it turns out that this J invariant has some special values. And in this particular case, this coincidence has something to do with the J invariant having a special value in this particular point. So it turns out to be an integer. So what is so special about these J invariants is that they have a number theoretical nature, and something called complex multiplication, theory of complex multiplication is dealt with these special values of J invariant, and it's very interesting because Hilbert said that it's the most marvelous thing in mathematics.
Why is this integer different from this integer?
Well, if you tell you, there is this constant term over there. Plug in that value of tau over there, that 744 pops adds to the print. There is a terminal 743.
Are you missing the zero then?
Where?
In the
value
bottom integer. Yeah.
Oh yes, it is.
That will almost definitely exist.
Too many things to be correctly. Anyway, so there are more interesting things about this. These functions, they pop up everywhere, basically everywhere. Whichever mathematical field if you consider here, you might be able to find modular form if you dig deep enough. So they will pop up in string theory. I don't know. And that is physics. I don't know. So what about the business of sphere packing? So sphere packing in 8 dimensions is a recent development by Marina Bielowska, which is under infringement, partial. So if you pack unit spheres in 8 dimensions, then if you do it centered around the E8 lattice, you get the densest possible sphere packing. E8 lattice means that if you sum up the coordinates, either they are even, either the sum is even, like the sum is even, and all the coordinates have to be integer or half plus an integer. So this is the E8 lattice. If you use E8 lattice for this sphere packing, you get the densest possible one. And there is a formula for the number of spheres which can be accommodated within a radius of root 2n from the center. It's this 240 sigma E of n. It is not random because we have seen this earlier. I tell you, yes, this is 240 sigma 3 of n. So Marina Bielowska used modular forms extensively to prove this result. It said that there are miraculous cancellations taking place, otherwise this would have worked. So there is a similar result in 24 dimensions, which is the Leach lattice, and this result followed after Marina Bielowska's work on sphere packing in 8 dimensions. So what about the other dimensions? People know very little about sphere packing in other dimensions. For 3 dimensions, we have this result by Hales, which was done in 2013 or something. And for 4 dimensions, I think it's still open. And we have somehow figured out things at 8 and 24 dimensions, and others are left open. So yes, Now we have some juice, inverted juice. So everybody knows about the famous last theorem. This A to power n plus B to power n plus C to power n is known on to be the integral solutions for the 2. So what does it have to do with modular forms? So back in the 1980s, I think, Frey found one connection with elliptic curves. Frey basically assigned this statement of Fermat's last theorem with this particular elliptic curve, and in this direction, Sarin Rivet proved that modularity conjecture, which is in our theorem, implies the Fermat's last theorem. So what's going on here? So very notable stuff is going on here. So what does modularity theorem say? Modularity theorem says that for every elliptic curve, there is an associated modular form. What do I mean by this statement? Everything is technical here. This term. So number of solutions. So if you reduce your problem, finding rational solutions to elliptic curves, you can reduce the problem to mod p. So if you count the number of mod p things in each elliptic curve and call it p minus cp, then this cp thing turns out to be coefficients of higher powers of q in modular form. So this is precisely what I mean by associated modular form. That means the mod p solutions, number of mod p solutions arise out of mysterious modular forms. So what did Sayer and Rivet do? They showed that if filter falls, then that Frey's curve, this particular elliptic curve, has no associated modular form. So that's the problem. That's the big problem. This contradiction, because what we already know by modularity theorem is that every elliptic curve has a associated modular form. So we have found a contradiction. So it must be that Fermat's last theorem is true. So some other use, number theory use, Langland's program. So in Langland's program, we try to understand the absolute Galois group of the rational numbers. This thing Q bar is the closure of the rational numbers, and basically we associate in Langland's program. We want to associate representations of the absolute Galois group with automorphic forms in GNN. Automorphic forms are just generalizations of modular forms. So in case n equal to 2, you get modular forms. The automorphic forms for GN2 are just modular forms. And for case n equal to 1, even for case n equal to 1, it's quite interesting. Gives rise to classical theory. It's a foundational theory for number theory, developed in, I think, 19th century or something. Late 19th century and early 20th century. So yes, so there is a big connection. Oh, so that modularity theorem is also a special case of Langland's program. It's a very tiny little special case. And even that is very powerful. Even that is powerful enough to solve the Fermat's last theorem. So this is something huge. So zeta function. Well, zeta function is very popular, so I just put it on that. So zeta of s is its interesting sum over the natural numbers, and we can define a corresponding function called xi of s in the following way. You have this gamma function, taking product of zeta function, and you have this product of I to the minus s over 2. There is a question mark over there. You can write it in the following way. This particular integral where theta of t is a theta function is a modular form. Modular form with a group which is not SL to Z. It's just you use another discrete. But anyway, they are modular forms. generalized modular forms. So why this question mark? Because it does not converge. Simply it doesn't converge. But you can play around with it and define it in a certain way that it converge. You split the integral between 0 and 1 and then 1 to infinity and play around a bit. You can make integrals. So using this integral and properties of theta functions, which is just modular function, using the transformation properties, you can find one functional equation relating xi of s and its symmetric image around half, that is xi of 1 minus. They turn out to be equal. Yes. And it allows you to define zeta of s analytically. Like, this is an analytic continuation of zeta of s over the entire complex field except one point. At s equal to 1, where there is a single pole. There is an associated Riemann hypothesis. Like for simplest possible case of Riemann hypothesis arises out of zeta function, but there are other Riemann hypotheses with possible L functions, I guess. So you have this interesting conjecture made by Riemann that all non-trivial zeros of the zeta function lies in the critical line, the real part of s being half. So there is a very old result behind it which proves that infinitely many non-trivial zeros lie on the critical line. And his proof made a heavy use of the fact that theta is a modular form. But in particular, this relation, this integral relation, he made use of this fact. Transformation forms, of course, dimensions. Okay, so something else. So this is the complicated looking product that was in the denominator of the G invariant. So it turns out to be a modular form with 12. If you expand this whole thing, you get terms like this, and define each coefficient to be tau and something. So Ramanujan noticed that these coefficients are multiplicative, but he couldn't prove it. He made some other conjectures as well, but I left them for this talk. It looks interesting. This one, basic as well, but it turns out to be quite deep. Not too deep, but just prove by modeling in Hackey operators. Hackey operators are just linear operators on the space of modular forms. The space of modular forms turns out to be vector space, finite dimensional vector space, and Hackey operators are studying linear operators. Then not all possible linear operators on the vector space. I can explain it without using specialized tools or something. But that's the best I can do. So there are other conjectures as well, and if you include other conjectures of Ramanujan related to this weight-well modular form, you get an associated L function to this modular form. And that L function also is a corresponding Riemann hypothesis, which I won't do yet. So modular forms of level 1. This is the most basic modular form that you can try to find. Level 1 means you use all possible transformation formulas. So all the elements in the group S equals Z needs to satisfy the corresponding transformation formula. So there are other modular forms which have a higher level.
You have 1 minute left.
Okay. So these are examples. Wait form, modular forms, wait 6. Basically, they have power 4 and 6 in that k term. Well, you can skip all these things. Just think that they exist, and that's it. So fundamental domain, it's an interesting patch of the upper half plane where every point is the equivalent, every point in the upper half plane is equivalent to some point in the closure of that particular connected open set F. And no 2 points in F are gamma equivalent. So it's defined for every possible discrete subgroup of S into R. And for SL to Z, our special case, it looks like this. Patch. Patch. Now, yes, counting the number of zeros of modular form in the fundamental domain, you can prove that the space of modular forms is finite dimensional of a given weight. In particular, weight 4 and weight 6 modular forms are one dimensional, weight 12 modular forms are two dimensional. And every modular form can be obtained as an algebraic combination between three. Weight 12 plus form, plus meaning that it vanishes at infinity. And you have this particular relation, like delta is obtained by doing this business, and it vanishes at infinity. But it also makes sure that it does not vanish anywhere else in the upper half. Anywhere in the upper half. So you can divide by delta of tau. Observe that this thing is weight 12, this is also weight 12, and tau is also weight 12. So you can get a modular function which is of weight 0 by dividing into same weight modular forms. And since they are linearly independent, this is non-trivial. And it turns out that every possible rational function, or every possible modular function is just rational function 0 tau. I think you get something from some periodic. Yes, you get some periodic modular.
So the next speaker is Shia, and she will be speaking on triangular partitions.
This is related to my IISc project, and this is also very introductory. So I'm going to talk about triangular partitions. So a partition of a non-negative integer n is basically just a way of writing it as a sum of positive integers. For example, if you consider 4, there are 5 possible partitions of 4. We can represent partitions as Gantt diagrams. So there are two conventions. This is the English convention, this is the French convention. I'll be using the French convention because my prof was French and we used the French convention. And so it's basically like if you have a partition 2, 1, 1, the order of the parts don't matter. So you just take it in decreasing order, then you have 2 blocks, you stack one on top of the other, you stack one. So what is a triangular partition? This is a definition which kind of is ugly. But basically what it is that if you consider the positive quadrant and you consider some x-intercept and some y-intercept, RNS, and you make a line joining them, then you consider all integer cells under the line. So any square which is completely under the line we will consider. Don't consider cells which are half above the line. Also, we will consider all the cells even if they touch the line. So if you can get a partition by this, so you always get a partition if you do this construction, but we can't get all partitions by this construction. So the partitions which you can actually get by this constructions are called triangular partitions. So a partition is triangular. There exists a line joining some r comma s such that there is a line joining these under which this partition lies. We say that this line cuts off the partition. That is the partition. So here basically, if I'm writing it this way, it's just instead of writing 2 plus 1 plus 1, I'm writing 2 1 1. So if you think about it, if you want to go from one partition to another, you will have to include a whole integer cell. So that means that if I have a line corresponding to a partition, if I move it by a small epsilon amount, it shouldn't really give me a new partition. It should still be for the same partition. So it turns out that for any triangular partition, you have infinitely many pairs of RS, that is infinitely many lines corresponding to each triangular partition. So obviously, if you have two lines which correspond to the same partition, they won't have any positive integer point between them. Otherwise, you'll end up including another cell. Right, so this is another example. So we saw that there are 4 partitions of size 4. So the partition 2, 2 is actually not triangular. So you can check this if you try to make a line to include this under it, either one cell above or one cell below here will get included. If you consider this example, I think it's very clear that whatever line you draw, this cell will get included. So a comment on notation here, later I'll be referring to these cells in terms of coordinates. So when I say 0, 0, it means the southwest corner of the cell is 0, 0. So this is 0, 0, this is 1, 1 for me. So the conjugate of a partition is basically just switch the rows and columns. So for example, if this partition is 4 to 1, I just switch the rows and columns, so that this is 4 to 1. Sorry, this is 3 to 1, 1. So this is 3 to 1, 1 like this. Yeah. So obviously if a partition is triangular, then its conjugate should be triangular. Because if RS is corresponding to this partition, then SR will correspond to that partition. So the slopes for these lines are going to be negative, and it's not nice to talk about the slopes in terms of these lines. So we'll just consider a vector orthogonal to the line, and we'll normalize it. So we'll get something of the form T1 minus T when we talk about the slope. So this is a staircase partition. When I say staircase, I mean the step size is 1. So for any staircase partition, you can always get 1 by 2, 1 by 2 as a slope. So now, if you look at this diagram, what we realize is that, as I said, if you have a line corresponding to a partition, then if you move the line around a little bit, you should still get the same partition. But then there is going to be some extreme end, right? So this blue line here, if I move it down a little bit, it will end up excluding this cell. And if I move the red line above a little bit, it will end up excluding this cell. So these blue and red lines are actually the extreme ends. But also notice that the blue line actually does not correspond to this partition, because this includes this one extra cell. So everything even slightly above this blue line and everything even slightly under this red line are actually slopes or lines for this partition. So basically we end up getting a cone for the slope vectors. A cone which looks like this. It's an open cone, and if you take the closure, you'll get a convex cone. So for any partition, you can characterize it uniquely by the size of the partition and these extreme lower and upper limits. So now we can actually explicitly give these lower and upper limits. So what I want is, for any cell in the partition, I'm considering the hook. So the hook is basically just the row and the column corresponding to the cell. So this is the arm, this is the leg length of the hook, and this is the arm length of the hook of the cell. So what I want is that whatever line I consider, this entire hook should be under that line, right? So if I find out the extreme values where this hook will be under the line, it will be helpful. So it turns out that it is going to be L here and A plus 1 here and A here and N plus 1 here. And these expressions are exactly the slopes of those things. And now I want this to be true for every single cell. So I just take the maximum over every single cell, and for the upper limit I take the minimum over every single cell. So partition is triangular if and only if we have a proper upper and lower limit for it. And this, if there is a slope vector which corresponds to the partition, then it strictly lies between the upper and lower limit. Right. So what happens is, so basically what is happening here is that if I have this lower limit, so if I am above this, I am getting the partition tau. If I am slightly below this, the cell gets excluded, and I again get a partition of the same size n, because this one extra cell is included and this one cell is excluded. So I am still getting a partition of the same size. So but at this exact line, I don't get a partition of size n. So basically, because there are finitely many partitions of size n, we will have finitely many such values where we don't get any partition, but below it we get a partition and above it we get a partition. So we are going to just have a bunch of cones separated by slope, single values of slope, which are finitely many. So now I want to define something called the dominance order. So So if I have two partitions, lambda, given by lambda 1, lambda 2, lambda n, and mu 1, mu 2, mu n, maybe. I'll just consider the rows above it to be 0 if n is smaller than n. So I will say mu dominates k if for any k between 1 to n, if I take the sum of mu1 to mu k and the sum of lambda 1 to lambda k, then this sum will be greater than or equal to this sum. This is true for all k. So that is the definition of dominance order. So if I consider the set of partitions of a given size, the dominance order is a partial order, like this, but this diagram is not nice. But so if I restrict it to the set of triangular partitions, I actually get a total order. The numbers are better. I just want the numbers to be good. So what I'm doing is I'm taking the triangular partitions of size 6 and I'm arranging them in the dominance order. And these are the cones of slopes. So as you can see, we get a very nice pattern. So basically, if you are in the dominance order, then that is your continuously varying pattern of slopes. And there is nothing corresponding to 1 by 6, 1 by 4, 2 by 5, 3 by 5. Lambda if the lower limit of this thing is above the upper limit of this thing, and it covers it if the lower and upper limit exactly match. So finally what we can conclude is that as we saw before, for any triangular partition we actually have a cone. So for any triangular partition the slope vectors form an open cone. So if we consider all triangular partitions of the size n, then you'll get open cone separated by rays. So you get something like this. These rays correspond to the boundary.
What do you mean by mu covers lambda? Like it's an immediate successor or something?
Yes, it's an immediate. So something nice now. So let's consider some line which touches the cell A minus 1, B minus 1. Now when I say that it is under it, so when I say that the cell is under it, what is happening is that this is the case, right? So, and I said that the cell is denoted by a southwest quadrant. So that means A comma B has to lie under it. That's why A comma B satisfies the equation of the line, and it can be rewritten with a bit of rearrangement as the equation of a hyperbola. So if you consider the positive RS quadrant, and we basically consider these hyperbolas for each of the cells, so you basically get a very nice figure, which I have to zoom in because it looks very bad here. I will do that. But the point is that this hyperbola is basically separating it into three sections. If you are above the hyperbola, then this cell is lying under RS. If you're on the hyperbola, it is lying under RS and touching RS. And if you're under the hyperbola, then this RS line is below the cell. So it does not cover. So, by below I mean it does not exactly cover it. Anyway, so the point is, if you have a hyperbolic wall, so if you're going towards the origin from here or from any direction, basically once you cross the hyperbolic wall, your cell A minus 1, B minus 1 gets removed from the partition. So every RS above this have partitions corresponding to them which have the cell. So yeah, so there is a bijection between these nice regions. So these are all the hyperbolas. We basically plot all the hyperbolas for all the cells, and there is a bijection between these sections and triangular partitions. So every single partition, this really doesn't. one partition corresponding to everything, and the diagram is really, this is for a larger, and this is in logarithmic scale. So, right. I'll just stop with this, I guess I can't show the slides. So, there are some definitions on the next slide which I'll just say. So we say that a cell is removable if you remove it from a partition and you still get a triangular partition. So this partition is triangular, and if I remove this cell from it or this cell from it, I still get a triangular partition. So these two are the removable cells, and a cell is addable if I add a new cell to it and you still get a triangular partition. So this cell is addable to this partition, and this cell is also addable to this partition. So basically, if you look at this, you will, yeah. So if two hyperbolas intersect at a point, that basically just means that this point corresponds to the line joining both these cells, the cell corresponding to this and the cell corresponding to this. So that is what the intersection points mean. And so for any cell, we can see that there is a whole region such that if you transition from here to here, you can do it without disturbing any other cell. So you can prove that for any removable cell, you will get a line such that you will get some RS such that it cuts off the partition and it only touches that cell in the partition. It does not touch any other cell. So yeah, that. And for any partition, you can have at most two removable and two addable cells. That means that these regions are going to have at most four sides. They can't have two sides because that would mean that there are two hyperbolas which are intersecting at 2 points, which means that corresponding lines are like so. It's not possible. So you can get only triangles and quadrilaterals here. Yes. So if a partition corresponds to an unbounded region, then it is going to be either the empty partition or a row partition or a column partition. But if you have a bounded region, it's going to be either a triangle or a quadrilateral, as I said before. So if you have a quadrilateral, if you see these quadrilaterals, these are really, really symmetric. So these points where the line joining two addable cells and this point which corresponds to the line joining two removable cells, so these all lie on x equals y. So it is clear that this line and this line are going to be parallel to each other. But that's actually true in general. For any quadrilateral region, the line joining two removable cells and two addable cells is going to be parallel. Now, if you think of triangular regions, so if I consider this triangular region, it basically has two removable cells and one addable cell. If I think of this triangular region, it has one removable and two addable cells. So what happens is, like, at least what is visible here is that these points which correspond to the line joining the two removable cells, there is no other hyperbola passing through them. So that is actually true. If you draw a line which joins two removable cells, you get no other integer point on it. Similarly, if you draw a line joining two addable cells, you get no other integer point on it.
2 minutes.
So this there is something I can't talk about, but I will have to explain too much. But I'll talk about Stromian. So I'll tell some other characterizations actually for what they're like. So if you consider a binary alphabet of 0, 1, a Sturmian word is a type of an infinite word, but we are actually concerned with Sturmian factors. So a factor is basically just a subword, but it has to be a continuous block. You can't have other things between the words. It has to be a continuous block inside this by definition. So yeah. So this is the definition of complexity function. So the number of factors of length n in an infinite word is the complexity function. But a word is Sturmian if you have a very very specific condition on it. This is actually the saddest character. If you want to know more, you can read on Wikipedia. I mean, if you see the finite mechanical word characterization, you'll actually realize why they're related to triangular partition. But like the point here is that one of the ways to check that a partition is triangular is that if I have a partition, if I write a word with, so let's say I'm calling every vertical step A and every horizontal step B. So the word corresponding to this thing will be so if this word, if the word corresponding to this is termian, then split partition is triangular. Here, there are more things which like they explain the motivation behind this. Oh, this is yours.
Next up we have Anmol Gadia. His topic is on a complex analytic proof of design number.
So my intention was to motivate juniors to complex analysis, but unfortunately I do not see a lot of them. So, like in real analysis, we have notion of differentiability. Just like that, in complex analysis also we have complex differentiability. So, suppose there is an open set, and on that open set of function f is defined, then if that limit exists, then that function is said to be holomorphic or complex differentiable, and that limit is denoted by f prime of z naught. And if the function is if this limit exists for all points z naught in the set, then it's holomorphic on the entire set omega. And like in real analysis also, we have functions which are nowhere differentiable. In complex analysis, even such simple functions like fz is equal to z conjugate are nowhere differentiable, because one can check that this limit happens to be different if you approach the origin from different directions. So, but what are complex analytic functions? So firstly, we understand what real analytic functions are. So real analytic functions are those functions which can be written as convergent path series locally. So for example, e to the x, you can write e to the x as 1 plus x square upon 2 and so on, x square upon 2 factorial and so on. And so it's an example of analytic function. So f is analytic if you can have this sort of a series representation for f, and a real analytic function you can differentiate it any number of times. So you can term by term differentiate this power series and it will still converge. And so real analytic functions are smooth functions in the sense that they can be differentiated arbitrarily number of times. So real analytic functions are smooth, but not all smooth functions are real analytic. So one can think about counterexamples. And similarly, complex analytic functions are those functions for which you can have power series representation in complex numbers. But the cool thing about complex analytic functions is that if you have a complex differentiable function, then it is analytic. So if the function is complex differentiable, then you can differentiate it any number of times. This is not true for real analytic real differentiable functions. If the first derivative exists, then the second derivative may not exist. But for holomorphic functions, they are always analytic, and you can differentiate it any number of times. So these are some properties of holomorphic functions, and an intuitive way to understand why all holomorphic functions are analytic, like how these properties of real differentiability and complex differentiability contrast so widely, because that is because if you go back, then in case of real differentiability, we have this h approaching 0 from two sides, either from the negative side of the origin or from the positive side of the origin. And if the limits are equal and both the limits exist, then we say that it is differentiable at that point. But in complex analysis, suppose we have the Argand plane, then we are approaching origin from infinite number of directions. So we want all the limits from all the directions to exist and equal the same thing. So this condition is rather stringent, and it leads to properties like this, that all holomorphic functions are analytic. So, and also if you integrate holomorphic functions over a closed loop, you get 0. And that is Cauchy's theorem. And similarly, Cauchy's integral formula is that you can write the function f in this form. You can integrate it over a circle, and this is not important for the talk. I have written down the proof for it. And as I said, you can differentiate holomorphic functions any number of times. So the nth derivative takes this form. This can be proved inductively. And this is a nice theorem about holomorphic functions, is that if you have a holomorphic function and it vanishes, and suppose it is defined in a region omega, and suppose it vanishes in a smaller subset of omega. So suppose omega dash is a subset of omega and it vanishes there, then we have that it is 0, it is precisely 0 on all of omega. So the values of function in the set omega, in the subset of omega, carries information about the values everywhere inside omega. So using this, we can talk about analytic continuation. So analytic continuation, suppose you have a function f which is defined on a subset of omega, and on a subset of omega dash, say. And the subset we are talking about is omega. So on omega, the function f is defined, and on omega dash, we want to extend it. So we have a smaller subset on which it is defined, but we want to extend it to omega dash. So we want a function which is holomorphic on omega dash and which is equal to f on the set omega. So we want capital F to be equal to small f on omega and to be holomorphic on omega dash. So this is known as the analytic continuation. If we can have such a function which is holomorphic, then that function is known as the analytic continuation of f into the region, into the bigger region. And this theorem is nice, that analytic continuations are unique. So if we have suppose two continuations of the same function, so suppose capital F1 and capital F2 are two continuations, then the difference function has to be 0 on the smaller set. So the difference function will be, since both of them are equal to f, small f, so they both have to be equal to f on the smaller set omega. So the difference function is 0 on omega. So by the previous theorem, we have that the difference function is 0 everywhere in this set omega dash. So analytic continuations are unique. So we get f1 is equal to f2 on omega dash. So next we have that. Next we have an important interpretation of holomorphic functions. For example, smooth functions, we can visualize that they are there are no sharp edges, or they are smooth. You cannot have sharp edges or corners in them. For holomorphic functions, we have this interpretation that if you have two lines intersecting at a point, and suppose they intersect at z0, and suppose these two are the lines we are talking about, and they intersect at the angle theta, then if this purple line gets mapped to this curve under f, and if this red line gets mapped into this red curve, then the angle between the two curves will still be theta. So this is a geometric property of holomorphic functions, and the subtle thing about this is that the derivative needs to be non-zero here at the point z0. So this angle preserving property is one geometric interpretation of holomorphic functions, which I really liked when I learned it, and so that's about holomorphic functions. And now we move to the prime number theorem. So the Riemann zeta function is given by this series. Sorry.
Yeah, does this property go the other way around? If there's a function which preserves angles everywhere?
Yeah. Such functions are known as conformal maps.
Yeah, so they must be holomorphic.
Yeah.
So like then does this angle need to be signed?
You can talk about. You can talk about the acute angles in both the cases. Acute angle in both the cases. So there will only be one particular acute angle between two curves.
Yeah, but z bar, the conjugate of z, wouldn't that also be conformal?
That is not really. It's nowhere holomorphic.
Yeah, but that preserves angles.
It doesn't preserve the signed angles between the lines.
So the sign is also important. Okay, so the Riemann zeta function is given by this series. For real part of this is greater than 1, and because when this is true, this series converges, and in that we can represent zeta of s by this series. And you all would have heard about this 1 plus 2 plus 3 up to infinity is equal to minus 1 upon 12. Right. So we'll talk about whether this is true or not. So I have borrowed this from 3B1B. This picture gets blocked out. Yeah. So here this represents the Riemann zeta function for inputs which lie on the right of real s is equal to 1, and in that region the vertical lines get mapped to these circles, and these horizontal lines get mapped to these union of semicircles. So since zeta is a holomorphic function in this domain, except for the singularity at s is equal to 1, note that the vertical lines and horizontal lines intersect at 90 degrees, and these images, which are the image of vertical line is a circle, and the image of horizontal line goes like this. These also intersect at 90 degrees. So this property is evident. This is evident from the angle preserving property, and so these horizontal lines get mapped to these things, and we can now extend this function in this set. So this is analytic continuation of the Riemann zeta function beyond the line real s is equal to 1, and you may want to draw arbitrary lines extending restrict yourself to drawing only holomorphic functions over here, then you get only one curve. So only one extension is possible for this Riemann zeta function because analytic continuations are unique. So and the analytic continuations looks like this. So we can now talk about the values of this Riemann zeta function for inputs lying here. So for that, there is some complex analysis involved. So we can write this thing in this form. We can, since this is holomorphic, we can write it like this, and the numbers Bn of x, if you substitute 0, you call it Bn, and they are known as Bernoulli numbers, and they come up in the evaluation of the Riemann zeta function at negative integers. So there is a nice recurrence formula representing Bn, the nth Bernoulli number, and zeta of minus n is given by this. So it turns out that zeta of minus 1 is minus 1 upon 12. So now if you just plug in minus 1 in this series, then this represents 1 plus 2 plus 3 up to infinity. And we say that that is equal to zeta of minus 1, but zeta of minus 1 is minus 1 upon 12. So if you naively just substitute s is equal to minus 1 in this equation, which you cannot, then you get this. So this is precisely to say that it's the wrong way of saying the correct thing. So zeta of minus 1 is minus 1 upon 12 is correct, but writing it this way is not correct because zeta of minus 1 cannot equal this. It's the analytic continuation which we are talking about at the point minus 1, which is not given by this formula. So now the prime number theorem. So prime number, the function pi of x denotes the number of primes less than or equal to x. So given an input, the number of primes smaller than that input, the number of primes smaller than that input is denoted by pi of x. So it's the prime counting function, and the prime number theorem states that pi of x is equal to pi of x goes asymptotically as x upon 1x. So the first proof of prime number theorem was in 1896, and that uses some complex analysis. So we first define this function, Mangold function, and that takes value log p at inputs which are prime powers and 0 otherwise. And that is not important. What is important is that you define psi of x. So psi of x you define by this formula, and why we need another function is that pi of x grows very erratically. So you can have twin primes in which case pi of x and pi of x plus 2 differ by 1, and you can have infinite series, like any length series of consecutive composite integers, in which case pi of x and pi of x plus r, where r is a very large natural number, will be the same. So the growth is very, it can be abrupt or it can be steady. So this function pi of x is not smooth. So we need another function, and what we do is that we sum for prime powers of x which are prime powers of p which are less than x, and we weight it by log of p. So this function turns out to be smooth, and so we can. It's easier to talk about this function rather than that function, and note that this function counts the prime powers weighted by some weight. So proving the prime number theorem boils down to proving that psi of x goes as x. So, and we further define another function, psi 1 of x, which is integral psi of x. So it is so the okay. So the prime number theorem boils down to proving psi1 of x grows as x square by 2. So this implies this, and that in turn implies phi of x grows as x upon non x. So and now this is where complex analysis pops up. So we have this relation between the zeta function and the function psi1, and here is where because this function you can write zeta prime of this by zeta of this. The negative of this is equal to so we saw convert function. So you can write, you have this equation. So this is related to the Mangold function, which is in turn related to the Chebyshev psi function. So this it is true that this holds, and the prime number theorem uses that zeta function is non-zero for all inputs of the form 1 plus it, and in fact zeta function has zeros, non-trivial zeros only at the line real s is equal to half. That is the Riemann conjecture. So here is when complex analysis pops up in the picture, and the rest it is just contour integration, and that is really complicated. So that is not something to be covered.
The I-infinity means that in the complex
In the complex
from
line?
minus infinity.
Yeah, it's a line parallel to the imaginary axis with real part 1. So that's all. So this is how the prime number theorem is proved. Yeah. Yeah. Okay, so you saw that zeta can be extended beyond the line real part of s is equal to 1, right? So now we can plug in minus 1 here in the zeta function now that it has been extended. So when you plug in minus 1, these are the calculations that you'll have to do, but you will get some value, and that value is minus 1 by 12. Okay, so this series 1 by n to the s converges only for real part of s is greater than 1. It does not converge for other side of the line real s is equal to 1. So this definition of the zeta function is not true there. So we extend it to another function, and that function is holomorphic. So that extension takes the value minus 1 upon 12 at minus 1. But that is not equal to this. So if we naively substitute s is equal to minus 1 here, what we get? 1 by n to the minus 1, which is summation n. And that is simply 1 plus 2 plus 3 up to infinity. So that is not equal to zeta of minus 1. But zeta of minus 1 is equal to minus 1 upon 12. So it's the wrong way of saying that zeta of minus 1 is equal to minus 1 upon 12. Okay.
One more thing. Can you scroll up in the Bernoulli recurrence that you showed?
The recurrence, the Bernoulli number recurrence.
Yeah. When you put like, even you expand, it's like NC and BN. It's like BN. BN and BN is like cancel out. How can you find BN with that?
But you have you have some terms from b0 to bn minus 1, right?
I mean, I guess it's saying the upper bound should be n minus 1.
No, I didn't think
Yes.
so.
So if the upper bound is like from k equals to 0 till n, then it will be NC and BN, and BN will cancel.
Yeah, even if it cancels out,
you won't be able to find BN.
yeah, okay. Okay, if we put n is equal to 2, then
We can verify this later. We
Yeah,
need to
if you
get
put
on
10
with
is
the
equal to
calls.
10, I guess.
Anmol.
Right, so the next presentation is by Sudarshan KV, fourth year. He will be talking about uh, class number of a number field.
I'll be talking about maybe what you'll encounter in some basic algebraic number theory course. Right, start with some preliminaries. A field extension is when you have one field inside another field as a subfield. So, for example, let's say our real numbers inside the complex number is a field extension. Q inside R is a field extension. So if you have an inclusion of fields, let's say a field L inside field K. So if you have a field extension, I write L over K to mean K is a subfield of L. So if you have a field extension like this, then L is a vector space over K. Right? And a vector space will have a dimension, it's either infinite or finite, and we denote it with this. You call the field extension finite if this is called the degree of the extension, if the degree is finite. Then there's notion of something called an algebraic. So let L over K be a field extension and let alpha be an element of L. If alpha satisfies some polynomial, let's see, if there is some non-zero polynomial with coefficients in K and suppose P of alpha is 0, then we say alpha is algebraic over K. And this extension is called algebraic if every element of L is algebraic over K. Talk about integral difference. So let R be an integral domain and let K be the fraction field of R. K is a field and you can look at some extensions of field extensions of K and assume it's algebraic. Then every alpha in L satisfies some polynomial equation in K with coefficients in K. Now we say it is integral over R if it satisfies some monic polynomial with coefficients in R. Then something called R is the fraction field. We say R is integrally closed if in this extension you look at the elements of K integral over R. So really all elements of R are integral over R. For example, if you take this satisfies the monic polynomial explained as R with coefficients in R. Right. So if the only elements of K which are integral over R and elements of R, we say R is integrally closed. Now one thing to note is every element L of L will have some minimal polynomial over K. That means the polynomial of least degree which it satisfies. But then if it is integral, the monic polynomial you are considering may not be that minimal polynomial. But there is a condition which says that if your integral domain is integrally closed, then it's sufficient to check the minimal polynomial. And you can, for an extension L over K, which are integral over R, let's call it S, then it turns out S is a ring, an integral domain with fraction field L. So basically we'll be applying this with R equals integers. So I'll talk about number fields, basic object of study. So number field, so usually we'll denote a number field with K and assume that K denotes a number field in this block. So number field is a finite extension of Q. So Z is an integral domain with fraction field Q. So you look at the integral closure of Z, which means, okay, since Z is also integrally closed, this ring of integers or the integral closure of Z is just the set of elements in K such that minimal polynomial of alpha has coefficients in integers. So, for example, you can consider the cyclotomic extensions Q of zeta n, where zeta n is some nth root of unity. This is a number field, and it turns out the ring of integers. That means the elements of this field, which are integral over Z, they are just. This is not really easy to show. It takes some work. However, a little bit easier to show is this field. You consider the field Q of root D. So you take some square free integer D and you adjoin some square root of it to the integers, to the radicals. So this is a number field, and the ring of integers is Z of root D, then D is 2 or 3 mod 4, and it is this thing, when D is 1 mod 4. So, I mean, getting the ring of integers is easy because you just have to check the minimal polynomial of an element here and check that the coefficients are in Z. So, in Z we have some kind of prime factorization of elements. So, every integer, rather non-zero integer is unique product of primes up to a unit. However, we don't have that in the case of number rings or the ring of integers. So what we do get is a factorization of the ideals of those number rings in terms of the prime ideals. So for that, we'll define what a Dedekind domain is. A Dedekind domain is a Noetherian integral domain which is integrally closed, and that every non-zero prime ideal is maximal. So for example, if you have some 0 is prime in an integral domain, and let's say you have some prime ideal P and you have another prime ideal P prime. This inclusion either means that P is 0 or P is P prime. We say that the height of the ring is 1. So we have a nice theorem which says that in a Dedekind domain we can factorize ideals as a product of prime ideals uniquely. And there's another theorem which says the ring of integers is a Dedekind domain. I'm not going to prove this, but what one shows in the process of showing that the ring of integers is an integral domain is that as Z modules, OK is just a free Z module of radical, where n is actually the degree of the field extension. We'll use this later. That's some something else about the numbering is okay, which is not there for an arbitrary dedicated array. That is, it has finite portions. So if you have an ideal I of OK, then when you quotient it out, get another ring. But it turns out that when I is non-zero, this thing is finite. So this property is called when a ring has this property, it is said to have finite quotients. Oh, we can just denote this size of this by the symbol norm of an ideal. And you can show that this thing is multiplicative. That means for any two ideals, this is true. Now if I and J are like co-prime ideals, this is always true. But in the case of number rings, this is true even for arbitrary ideals I and J. So the ideals of this number ring, we call them integral ideals. There's another type of ideal we look at, it's called fractional ideals. So basically you take an ideal I of the number ring and you scale it by some factor. So these things which are like submodules of the number field, you call them fractional ideals. So the way you define it is kind of like J submodule of K is fractional ideal. If there is some alpha such that alpha J is an ideal of OK. So essentially the same thing, you are scaling some ideal by some element of the field. And now it turns out that these ideals, they have a lot of multiplication reasons. So you know how to multiply two ideals. Just take products of their generators and consider the ideal generated. It turns out that remarkably this operation will give you a group law on the collection of all fractional ideals. So for example, associativity of the product is trivial. Your identity will be played by the role of this ring OK. So that means just like for any ideal, fractional ideal J times OK is just J. And then this is clear. The non-trivial part to verify is that every ideal has an inverse. I'm not going to do that. But the inverse is just given by this thing. You take all elements of the field, which when multiplied by I, you get a subring of an ideal of OK. We'll denote this group with JK. A little bit easier to see is that if you have some principal fractional ideals, which is like alpha times OK or some alpha in K. These are the principal fractional ideals. These things form a subgroup of your group of ideals, fractional ideals. So this is easy to see. For instance, you take alpha times and the inverse of the ideal generated by alpha is alpha. The ideal generated by alpha inverse. So we have an inclusion of abelian groups. We have an inclusion of abelian groups like this. So when you quotient out, you will get a group. It's called the ideal class group of a number field. Can you see this? Assume you can see. Anyway, so first main theorem one encounters in algebraic number theory is that the class group of a number field is finite.
Principal fractional ideals means like one by b, right? Principal fractional ideals just means like how do you like
Principal ideal is generated by one element.
the general structure for them of those two
Like this. Generated a single element of the field. So I'll spend the rest of the talk proving this. Okay, once again I'm going to skip a lot of stuff, but I'll give you the general idea of it. There's another description of the ideal class group which is slightly easier to work with. And you can draw the equivalence a little bit easily. So we say you take the, so let JK be the group of fractional ideas. And you say I and J are equivalent. So I and J are two fractional ideas. You say I and J are equivalent if there exists some alpha, beta, non-zero. So that alpha is, I mean, this bears some similarity to the quotienting out by the principal ideals. So this thing turns out to be an equivalence relation, and when you quotient with this, you get something big. You get the class group, right? Now, equivalence classes in this are called ideal classes, and so the good thing about number fields is if you have some bound lambda, then you look at the number of ideals with norm less than lambda, less than equal to lambda, then the number of ideals is finite. So I am talking about integral ideals here. It's easy to see that every ideal class will contain some integral ideal that uses some finite generation of ideals. I'll skip that. Right. So now if I show that each ideal class under this equivalence relation contains an ideal, integral ideal, satisfying this bound for some lambda. So I mean I fix a lambda and I show that every class contains an ideal for which this bound holds. Then since there are finitely such ideals, right, there will be finitely many ideal classes. This will be our strategy. That's another nice condition which leads to this condition. Right, if you have some constant lambda and there's this property that so here I am talking about integral ideals. So every ideal J contains an element alpha non-zero such that every non-zero ideal J such that you take the norm of the ideal generated by alpha and compare it to the norm of ideal generated by J. You have this bound for some lambda. If you have this thing, then that would imply that every ideal class contains some ideal I with a norm less than equal to lambda. So you can see the proof here. Okay, maybe one thing I should remark is that in Dedekind domains, since you have unique factorization of ideals, an inclusion of ideals, non-zero ideals, gives rise to an ideal. This gives rise to a factorization like this for some other ideal. So the inclusion is same as dividing. Yeah. So I have to show that every ideal class C contains an ideal with norm less than equal to lambda. Right. So choose some class C and take an ideal, integral ideal J in the class C inverse. Then take any alpha here, take such an alpha so that this bound is there. Right, now you have an inclusion like this, alpha inside J. So there is some divisibility, which means there is an I so that this is Ij. Right, and this I will belong to class C because Ij is principal. So then this is multiplicative, so cancelling out the J will give you the norm of I is less than equal to lambda. 2 more minutes. So we are just producing such a lambda for which every J contains some contains contains an element for which this holds. Yeah, and okay, so recall that I said okay, this isomorphic to Z to the n. So we can pick some kind of basis of okay, Z basis of okay. Which means, let's say alpha 1 up to alpha n. It's a Z basis. Right. Now it turns out that using this quantity, so you know there's some technical condition called separability. And so like the number of embeddings of a number field in complex numbers, the number of such distinct embeddings is equal to the degree of this over k. Yeah, and just assume that there are n such embeddings, and then you consider this sum. We just need to show that every ideal J contains an element alpha for which this inequality holds. The main part is using Eisenhower principle somehow. Maybe I'll just leave this lambda. So let J be any idea. And you have some kind of now we had an integral basis alpha I, so you consider all like linear combinations with these mi's being integers between 0 and m. Then there are m plus 1 to the n such elements. These are in OK. There are m plus 1 such m plus 1 per n such elements, and the size of this is more than the size of this quotient. So that would mean that two elements here map to the same element in the quotient by Pieterburg principle. If they map to the same element in the quotient, that means their difference is in the ideal J, and the difference is non-zero. So you have an element alpha, which is again I'll abuse. You have this thing, but each mi is between 0 and m. So here also you will have something like this. And when you look at the norm of the ideal generated by alpha, this actually turns out to be the norm of the element alpha. And this thing is by definition the product of the sigma is of alpha, modulus of the sigma is of alpha. Once you use this thing, you use triangle inequality. Like sigma of alpha is just sigma j of alpha is like summation of sigma j of mi alpha I. Like sigma is a ring homomorphism. Once you pull stuff out, you get this summation, and each mj has size less than equal to m. So when you pull that out here, you get n different m's. So that's your m per n. And recall that this part was your lambda, and m per n is less than equal to size of that. Yeah. So we have shown that every ideal contains an element alpha such that this norm of alpha is less than equal to lambda. So this will show that the class number is finite. Thanks for
That was like 7 lectures of algebraic number theory in 20 minutes. Okay, so the next talk is by Aviral M from 4th year. He will be talking about algorithms for viral marketing.
While making the slides, I was thinking what would be the appropriate level of prior knowledge to assume from a group of mathematicians when talking about theoretical appears the answer is none. So I'll be going from the beginning. So yeah, if some of you know some of this, then well, I'll just go through it again quickly. Right. So we're starting with what is the directed weighted graph. Okay. So yeah. You have nodes. You have edges between the nodes, and now since it's there, right, these edges have directions. So now it just means that there is an edge from him to him, and not the other way around, right? Directions and weights. Well, weights is just a function from the set of edges to the real numbers, which just means that each edge has a value. It's not just an edge; it has a number associated with that as well. Okay, and then what does we need to know? Weakly connected, strongly connected. Weakly connected means that so given any two pairs of points, there is either a path from A to B or B to A. Strongly connected means that there is a path from both A to B and B to A. Strongly connected components. If your graph is not strongly connected, but it is weakly connected, then you can have components of equivalence classes of all points which are strongly connected with each other, and those are called strongly connected components. And then you have observing components. Now, what is the observing component? So this is kind of non-trivial. So let's say you have a set like this, right? A graph here, and then you have this, and then like something like this, okay? And now it turns out, so from this point, there are no edges going out. So this is observing. This is an observing point. Now, if I look at say this set, right? These 4 points, there are no edges going out of the set. So all the edges are within the set itself. So this is the observing set. So okay, so now that's the observing set. So now what's the observing component? It's just a strongly connected component that is absorbing. Okay, so once you break down your graph into equivalence classes of strongly connected components, some of them will be absorbed, and those are called absorbing components.
Can you explain strongly connected components?
Okay, so let's say you have, so here the whole deal is that the edges here are directed, right? So if you had an edge from A to B, you need not have it from B to A. So now it's possible for me to be able to go from point A to a point B, but there might be no path to go from B back to A, right? So in such a graph, it's not called strongly connected because the connectivity is not that strong. It's only one way. But if any two pair of points, you can go both ways. So if you can go from A to B and from B to A, that is called strongly connected. It's a tighter notion of connectivity than B to A. And then the next one is periodic graphs. So this is to do with the cycles on the graph, right? So now the definition is that if the length of every cycle in the graph, if the HCF is not 1, it's called periodic. And so the main thing is basically that. So let us say I have this nice graph here. I'm assuming people can see the dots I'm making. I'm wrong in this assumption, but it's not clear. Yes. But at least you can see the lines, right? So that's good enough. Now, okay, this. Right, I have 2 cycles. Well, okay, this is one cycle, and this is one. No, it's not a cycle. Yeah, okay. I have 2 cycles, and they're both of size 6. So the HCF is 6. So the period of this graph is 6. And now, what is so great about it being 6? So let me number these, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Okay. And then if I create a set which has 1, 7 and 2, 8 and 3, 9, 4, 10. What am I missing? Okay, 5 and 6, right? And I take the and I contract these points to single points, then I get a single cycle, right? So this is what periodic means, that there are equivalence classes which you can contract to get a single cycle, and that is what a periodic graph is, right? So this is all you need to know about graphs. The next thing is about social networks. So what is a social network? It is just a name we give to a graph when we use the graph to observe people, right? And it doesn't have to be people, it can be anything. But so if we have some agents and we have some interactions between the agents, and then through these interactions something is spreading, or like, maybe it might be information that is spreading, or it might be a virus that is spreading, and when we want to see these things, right, we call it a social network, right? It's a network between people. And so this can be used in epidemiology, for example, to study the spread of a virus, or by computer scientists to study the spread of information or rumors, right? So when we talk about the spread of information, right, we use the term diffusion often. And so let us say that some nodes initially have some information, and then their neighbors, and we define some processes through which their neighbors can get the information from them. Right? This can be deterministic or probabilistic. So for example, one example for deterministic is that so if the majority of your neighbors have an opinion, you will also get it. Okay, so for example here, let's say he has two neighbors, and ignore red and blue for now, just say that they're both opinions. Okay, so he has three neighbors and two of them are colored. So he is going to become colored next, right? So that is the majority model. If the majority of the neighbors are colored, you will become colored. Then you have a probabilistic model called the voter model, which is that in each turn, you pick a random neighbor and just take his color, right? So you pick a random neighbor, if he is colored, you become colored. So that's a probabilistic model. And then you can also have like two different ideas, red and blue, right? So maybe two opinions saying that this is good or bad, and then uncolored people just don't have an opinion about that thing. Okay, so here it's called the independent cascade model. Both red and blue are spreading independently, and then you can stay red for a while, and then you can become blue, and then your opinion changes, right? And all that happens. Okay, the next thing is Markov chains. Right. So this is So when this process is probabilistic, right? So you have a state, right? So for example, you have this coloring here, right? This is one state. And now let us say we're taking the voter model, right? And these bolded arrows are the ones that were picked in that time step. So this V2 picked V1, and so V1 was uncolored, so V2 also stays uncolored. And then the same way, so V3 picks V4, right? And then V4, this diagram is wrong, my bad. Okay, V4 picked V5, so V4 should have been blue. But yeah, you get the idea, right? So it changed. But then, if you had picked someone else instead, the coloring would have been different. So this is probabilistic. So now there's a probability of what the next state is going to be given a certain state. And so when you want to look at these probabilities, you get a Markov chain. So each state, each coloring is a node, and the edges between the nodes are directed, and the weight is the probability of going from the first to the next, right? And okay, so a Markov chain is a special type of directed weighted graph where the sum of the out edges of each node is 1. Okay, yeah, and now observing components exist. So in a Markov chain, the observing components are basically places where, so if the process is going on, you will enter an observing component, and then you won't be able to get out of it. So the process is still going on, and it might go ad infinitum, you'll keep going in circles, but you're never getting out of that component. And the good thing is that it is the smallest such component for which this is true. So which means that once you get into an observing component, you will eventually keep going to every member of the component. Okay? So that is the smallest restriction you can make, and so we say that the process has then converged. And then the size of that component is the period of convergence. Okay? Yeah, and then there are some nice types of Markov chains. So there's a property called the ergodic property, which gives you kind of a stationary distribution and then tells you, so these are some things that you use when looking at the convergence of Markov chains. Okay, so we are looking at graphs and yeah.
How do we know that the period of convergence is going to be the size of the component? There could be multiple connections inside the component that make it non.
Oh no, yes. So actually, so the period is the word used for the size of the converging component. So I'm not saying that it is going to visit each term in the each state in the component once in that many rounds. Right? That's not what I'm saying. I'm just saying that that is the size of the component. The period is the name given. And so if each edge was of equal probability, you would get that the expectation value would be one by that thing, one by the number. So that's why it's called the period. But yeah, the period is just a name given to the size of the component. It is in no way related to how often it comes back to that point. Yeah. Okay, so now we have looked at some graphs and Markov chains and graph properties, right? Actually, I'll just cover another interesting property of periodic graphs, right? So, right. So now, like I said, you can take equivalence classes such that the nodes, the edges are only going to be from one to the next class, and this forms a cycle, right? So all the edges are going to be from members of this class to this class. So you have cyclic ordering of these independence classes. which also means that each of these are independent sets. Each of these classes, there are no edges between them. Okay, but it also means that every path between any two members of the same class, so has the length of that path has to be a multiple of the number of classes. Because you only come back to this class once. So in this example, only once in 5 steps, I'll come back to this set. So every path from any point here to any other point here is going to be a multiple of 5. And now, if you define a new graph on just this path, where I say that I have an edge from one node to another, if there is a path of length exactly 5, right? So that is going to give me a new graph. This graph is going to be aperiodic and strongly connected. So each of these will form a separate aperiodic strongly connected graph if I consider edges to be paths of length exactly 5. If I in this case, period in general case. Right? So that's another nice property. And then we move on to algorithms. Right? So yeah, what are greedy algorithms? So a greedy algorithm is so it is a kind of programming where you start off with a solution and you have a guarantee that increasing the solution in a reasonable way is going to make your the answer you get better. Right? So when you have that kind of property, you can try using a greedy algorithm. So some examples are interval covers and spanning trees. Where, so for example, for a spanning tree, you start off with the empty set and then one by one you start putting edges such that you don't form a cycle, and finally you get a spanning tree. Right? So those are greedy algorithms. And another kind of algorithm is the approximation algorithm. Right? So yeah, so here the notion of hardness comes in. So some problems are known to be NP hard, which means that you don't have any polynomial time solution to them, right? So then instead of coming up with non-polynomial algorithms, what people like to do is they like to see how close of an answer can you get in polynomial time. So I can't get the exact answer, I can't get the best answer I can in polynomial time. How much can I get? What guarantee do I have? So like for example, if I can't get like the optimum answer in polynomial time, can I get at least 90% guarantee that no matter what input you give me, the output I give you will be at least 90% of the optimum answer. So that is called approximation algorithm. And so this is a important one because it's one that I used. So it's called hill climbing approach, and it tells you that if you have a monotone and submodular function, then you set function, then you can increase the set and come up with a 1 minus 1 by e guarantee. So okay, what is monotone? What is submodular? So now, let us say I have a set, and this set. Okay, so okay, first of all, right, I have a function from every subset of edges to a real number. So it takes any subset of the nodes. It takes any subset of the nodes and gives me a real number, right? So this is my function. Now, what does it mean to be monotone? It means that if, say, S is a subset of S dash, then f of S is less than equal to f of S dash. Okay. Now, what is submodular? What submodular means is that the bigger my set gets, the lesser chance I have to improve. Right. So, let us say that I have S and I have any W belonging to V of G. Right? Any extra node W which is not in S dash. So it's not already in S dash. And I have S and S dash. Okay? So the improvement I get on adding W is going to be f of S union W minus f of S. Yeah. Okay? So this is the improvement I get to S on adding W. And this is going to be greater than or equal to the improvement I get on adding the W to S dash. Okay, yeah. So as long as I increase a set and I get a better value, and bigger sets have harder to improve on than smaller sets, right? Then my set function is monotone and submodular, which means that I can use this algorithm and get a 1 minus 1 by e guarantee. E is the 2.78 thing, so this 1 minus 1 by e is 63%. Okay. Yeah, so that's an example of an approximation algorithm. Okay, so now here is one algorithm I worked on, which is called seed node optimization. right? So the question is that we start from an initial coloring, right? And then we go to the mark option and we converge. And now when we converge, we get some distribution there, saying that it's going to spend this much time in this state, this much time in this state, inside the absorbing strongly connected component. Okay. So now, if we weight it on that, if we weight it on the probability of it being there, right? We weight it by the distribution. This was before that. So now let us say that I have a certain payoff for each state I'm in, right? So for example, let us say that I sell toothpaste, okay, and every month 100 people come and buy toothpaste. They either buy from me or they buy from my opposition. I forgot what's the marketing term? Competitor. Yes. They either buy from me or they buy from my competitor, right? So now every month I want I want more people to have like the opinion of my brand than his brand. So let's call them blue and red nodes, right? So every coloring has some blue nodes and some red nodes. Now I want to maximize the number of blue nodes, right? So then we have a function which from the all states to the real numbers, which is basically the number of blue nodes, and I want to maximize that, right? So if there was an initial coloring, finally in the distribution I can weight it by the number of blue nodes in each. So if there was a 50% chance of being in this state, state A, and A has 20 blue nodes, and there's a 50% chance of being in state B, and B has 30 blue nodes, then my final payoff is 25, because on average 25 people are buying from me, right? So, and this expectation is what I want to maximize, and to maximize that, okay, so what can I do? I have a budget, right? When I first started my company, I went to a Shark Tank and I told them, sir, I'm selling toothpaste. They said, oh, very original, here, take some money for advertising, and they started advertising my product, right? And then, so now, but I have a limited budget because that money is not mine. And I can't go to Shark Tank again, they banned me. So then, I have that money, and there are certain number of people I can advertise my product to using that money. So, with the limit K, right, on the number of people I can initially turn to, what is the highest expectation I can have? So there's initially a graph which has red and white nodes, and I can turn some of them blue. Which nodes should I turn blue to maximize this? Right? So that's the question that I want to answer. And well, so there's an easy reduction to a known NP-hard problem, which is basically the set color problem, right? So if you have a big set, right, and you have a bunch of subsets, and you can only choose K of these subsets to maximize the union of these K subsets, which K will you pick? That's a known NP-hard problem, and so there's an easy reduction from this to that, which tells me that this is NP-hard. So I don't want to waste my time going around finding a way to do it optimally. So yeah, I want to do it suboptimally, and it just happens that this function, right? So the set function is the initial set of blue nodes to this final expectation, right? So this is the set function, right? So I start with a set, which is the initial set of blue nodes, and I end with a real number, which is my final expectation. So this set function happens to be monotone and submonitor, which tells me that I can use my hill climbing approach to get a 63% approximation on this, and so I do exactly that. I modify the algorithm to do this, and to at each step find which node I should add. So I start with the empty set, and at each step I find which node I should add to maximize, and I keep doing that. So for example, I start off with the empty set, and I find out that this guy as a singleton gives me the best expectation. So I say okay, and I add him to my bucket, and I say okay, along with him, what's my best pair? So it turns out that this guy and this guy is my best pair. So I add him to my bucket. So I say okay, I have these two, who should be my third guy? So among the rest of them, adding this as the third guy gives me the best increment. So I do that, and so I do that K times, and I get K people who at each step give me the best increment, and I have a set which is guaranteed to be at least 63 times the best possible answer. And so some applications of what I just told you. So one is marketing, where I'm doing targeted advertising and I want to maximize my sales. The other is campaigning, right? So let us say I'm a party man and I want to go door to door and tell people about the glory of our great All-Father Modi, and then Like those people, let's say they listen to me. Okay, let's say I'm a very good like orator, and they listen to me and they agree that Modi is the man for the future of India, right? And then who should I go and talk to? Because I'm a busy man. I have limited time. I can only talk to this many people. Who should I go and talk to so that I maximize the number of votes that BJP gets at the end of the day, right? So that's the second use case. And the third is vaccination. So it turns out that if these people maximize the spread, then the same people will also minimize the spread if I vaccinate them, right? So this same algorithm can be used for vaccination to this thing, yeah. And okay, so that is it about my project. Should I also talk about? No? Okay, I'll skip that then. Yeah. Thank you. Any?
Just one question. If you know the graph, you have an algorithm to determine everything. But how do you find the graph in the first place for campaigning, for vaccination?
So there are things you can do. First is surveys. Second is paying Facebook Mama. Third is so the third thing is the most mathematically interesting thing, which is low information variance of this. So the same thing, right? If you can show that it is still monotone, where you don't know some weights. So you take the whole graph, okay, and most of the weights are like constants. Some of them are random variables, okay, and then you do the same thing, and you say that, so you now have a distribution of that weight. So this distribution will just become a more distribution, but the expectation is still an expectation. And if that still turns out to be monotone as a modular, you can do the same thing.
So when you do run this algorithm on, let's say, I mean, of course not a typical graph, but if you run it on graphs that have a significant proportion of red dots to begin with, do you see any sort of underlying principles of what kind of nodes are the optimal nodes to select as blue for your first month? Is it like nodes that are at the border, or do you like spread them equally among the...
Right, okay, so it depends on your budget, right? So if your budget is very low and you have 7,000 nodes and you're only turning 10 of them, then it makes sense to have this prefab part, right? That's what you notice. But then if it comes to like around 50%, what you start noticing is actually very interesting, right? That this performed very well was that, so you pick the highest in degree node and then you form an out degree ball around it. So let's say this is the highest in degree node, and now these are his out neighbors. So you color him blue, you color all of his out neighbors blue, and you color all of their out neighbors blue, and you do that until you run out of budget. So it's basically that you kidnap the highest in degree guy and protect him with as many layers as you can, because he's your man.
The next talk is by Aviral Sood from the 4th year. He will be talking on glance at modern partial differential equations.
What if you introduce an element of, randomly some people will change their opinion, like some epsilon probability of randomly changing your opinion, your board of brands like that.
Okay, so you're saying that none of my neighbors like the opposite
Yeah,
side?
like you're protected, you're the man, but still you suddenly change your opinion. Okay, I mean, it can be changed back, but like...
So at the end of the day, that's the number.
Of course.
Right, and then you're saying that there is also a small positive going to a state.
Yeah.
Then the markup is not as fast because there are lots of it. So everybody can randomly turn. Okay, so this is the markup. But then what really interests us is that is it still modular? Okay, and so as long as this is the independent house, having more blue people still helps, right? So as long as more blue people and all of them can turn on the board, it still like helps to have more people, and the more people have, the lesser increment. So I think it will still work.
Yeah, so I will be talking
modern glance like that. So this you will probably not see in the first person TV. You might see some people talking about it, depends on who's teaching you the course. So let's start with what are the questions in PD. So PD of course arises by modeling physical systems. So there are physical systems, we have PD modeling them. We would have some initial conditions or some boundary conditions and we would like to know how they evolve or information about the whole domain, whatever we are working with. So what would we want? Our PD model should tell us that there is a solution. So existence of a solution is important. We would also want it to be unique because as we repeat this experiment many times, if we have the same initial parameters, then we expect to see the same function, same solution as coming up again and again. Hopefully it doesn't change when we repeat the experiment. And then there is continuous dependence on initial parameters. So this is physically relevant in the sense that if we have a physical system, what we have access is to a measurement of the initial parameters. This is just an approximation. There will be some error about this initial parameters. And we don't want it to propagate and become too large. So since we have a error range around our initial parameters, even a solution should be in a small error range. So that is why we would also be interested in continuous dependence on the initial parameters. So let's start with the PD. So one of the most basic ones, most widely encountered one is the conservation law. So we will be looking at the this one. This is the general form of one. This is first order PD. That means there is only one derivative at most in the equation, and it is. We would also be interested in a non-linear one because linear tend to be easy, not always, but we want to see something interesting. So we will take non-linear PD, and this is in only one spatial dimension. So there is the time variable which is from 0 to infinity, and we have a space dimension which is all of R. So there is a toy model which people like to work with when first looking at this class of PD. It is known as the Inviscid-Burgers equation. So this is the case where you take capital F to be x square by 2. So u square by 2, j2, you get u ux. By the way, t is time derivative and x is the x derivative. So this turns out to be one of the most simplest and the first one where you see some non-trivial phenomenon happening. So why is this equation important? Another reason is that it is a simplified version of the Navier-Stokes equation. You get this equation if you take the pressure term to be 0 and also take the viscosity to be 0. That is why in this. So can we gain some information out of just this? Let g be some initial g function, and we want to gain some information. So suppose this is our domain. This is the time axis, the x-axis, and we have some point over here somewhere. Like that, the x-axis. And we know what our function value is along the x-axis. We know some g. So suppose we could somehow get a path from here, some path, hopefully continuous path, and we reach the initial boundary, and we know the value over here. Suppose this point is x0. We know that g of x0 is the value of the function here, our solution, which I have denoted u unknown function. So if we could somehow compute the value of the function along this path, and we know the boundary, the value at one endpoint, hopefully we can get it at the other endpoint as well. So let's try doing that. So suppose we have this path being parameterized by some x of s from s, and I will denote g of s to be equal to u of x of s from s. So that means that z is tracking the value of the unknown function along this path, and it is a function of just one variable because that is the parameter which is traversing for us through the path. So what can we do is just this. So first let's take the derivative to see if there is something happening. So this is the derivative with respect to s. This is the normal multivariable chain rule. You take the x derivative, multiply the x derivative with respect to s, and that a time derivative. Now remember that our equation for the scalar conservation law was something like this: ut plus f with the x value. So this term is the same as just dx f prime of u, singularly, f prime of u times the x derivative. And this is almost like that, except that we have an x dot of s there. And suppose our path was so nice that x dot of s was equal to f prime of u along this path. So f prime of u would be the original equation, the equation we started with, the conservation law. And suppose that x dot happened to be equal to that. Then substituting that in z dot, we get 0 from the PD. This is the first place where we have used that this is a solution to the PD. What does that mean? That z must be constant with s, because the s derivative of z is 0. So suppose it is some u naught, some constant u naught. Putting that back in the x dot of s equation, we get that x dot of s is f prime of u naught. But we know the value. Of u at the boundary, that is at time 0. So first, x dot of s is equal to f prime of u naught. Since u naught is a constant, f prime of u naught is also a constant. Integrating that, we get x of s as a straight line with respect to s. And u naught being the initial value, is x of s is equal to f of g of x naught. So what does this mean? This means that along these straight lines, so you have x naught, you have a straight line emanating from it. Along this line, the value of the function is constant. That is what it means for z dot of s to be 0, z of s to be u. So, our function u is constant along these characteristic curves. These straight lines, for our case, they turned out to be straight lines. They are known as characteristic curves, along which you can think of them as being curves along which the function is easier to compute. In our case, it happened to be straight lines, and it also turned out to be that the function is constant along these lines. Very nice ones. So, where do problems start arising first? So far, I have not shown you anything which seems to be problematic. What is the problem in this? Where can problems arise? So, I will tell you a small story which you might hear if you take a course by someone over here. So at the time, fluid mechanics were modeling some airplanes flying in the air, stuff like that. And for a long time we thought that objects moving in air cannot break the sound barrier, because their equations told them that as the speed approached the speed of sound, the drag force would increase 10 to infinity and stop the motion from happening. Then someone built the Mach 1 aircraft and flew. So then we had to abandon the notion. We had to abandon our notion that PD was our classical formulation was enough. We needed something more. When the object breaks the sound barrier, there is a genuine discontinuity across the shock profile. There is a sort of a barrier, some region, on either side of which the fluid has a different velocity. There is a sudden jump. So if our models have to tell us anything correctly, at the very least we need to be able to accommodate discontinuities into them. But right now our equation requires the function to be at least differentiable. So we need to do something which will allow us to somehow accept discontinuous solutions as well. This is what is known as a weak formulation of PD. So I'll start with this one. So this is the equation we have. Suppose I multiplied by a smooth function some phi. And by smooth I mean infinitely differentiable. Let's say compact support as well. That just means that outside a small enough set, this function is 0. And we will integrate this to see if anything nice happens. And we will use integration by parts. For the first term, when we do this, we have the double integral and do phi t. So the time derivative is over here. We get some boundary term, but because we have
other term as time tends to infinity is 0. This is the other term. And similarly for the last term over there. This is 0. So this is just integration by parts. This has a boundary term, but because we are assuming compact support, that means as you go outside, as your boundary, as you range over all the reals, that term just goes to 0. So what do we do with this? We have this equation. Notice that this equation makes sense even when u is not differentiable. It doesn't even have to be continuous. All we need is that u is bounded. If u is bounded, we can make sense of all of these integrals. These are initial function by the way. So this makes sense for that. So now we do something peculiar, I guess. If there is some u, some bounded function u, for which this integral equality is satisfied for all these smooth phi, then we will call it a weak solution of our original PDE. This is the central notion of weak formulation. This was done by Leray around 1930s, which is very recent for mathematics. And see that if u is smooth, all of these integration by part steps can be reversed because I can now send the derivative back, reverse it, and get back to this equation again. And this is true for all phi. That means that the PDE is satisfied. So if u is smooth, then weak formulation is just the same as the regular classical notion of whatever it means to be a solution. So now, even now, I have just told you that we have been able to accommodate discontinuities because our this thing can still make sense, even if u is discontinuous. But what we have done now, we were looking at smooth functions earlier, once differentiable, that's it. Now we have a much larger class of solutions which we could look for, we will check this equality if it holds or not and all that. We have now defined a new existence of solutions, but we might not have uniqueness now. That might go away. But I am still not showing you where they can arise, so let's do that. So earlier I showed you the characteristic, the lines of characteristics which were straight lines for us. And for the Burgers equation, they just turn out to be this. So you take a point here, you have the slope g of x naught. Because this is t and x, you flip the slope or whatever, and you get some line. You can do this for all points on this. So suppose I start with an initial function which is discontinuous to begin with. And let's say it is minus 1, 0, 1. We will get these lines. So what does this mean? That if you pick any point over here, you can find a straight line, go along it backwards, reach the x-axis. You know the value here, it is minus 1. So the value of the function is minus 1 all over here. Over here you do the same thing, you have 1 over the value of the function being 1 everywhere. But this region doesn't have any characteristic planes. We don't have any information about that at all. That is a problem because we cannot draw any more characteristic planes. These are all of them. But there is the other extreme of this. What if you flip minus 1 and 1 and the characteristic intersect? So in this region again, there is no problem. You pick a point here, you go backwards, you will reach the x-axis, you know the value. Do this here as well, but here they cross. So you have a choice between the two lines you want to pick. You go along one, it tells you minus 1, you go along the other, it tells you 1. How do we resolve this? So this is where the shock waves, the discontinuity will now come out. So there is a way to resolve this. This is called the Rankine-Higuiot condition. So let's see the simplest case of where things can start going wrong. So suppose there is some place and you have some curve in it that you were lucky enough that a solution is not smooth, but at one side of a curve, some smooth curve, this solution is smooth, and over here as well it is smooth. So on the left of the curve we have a smooth solution, on the right of the curve we have a smooth solution. The discontinuity arises along this curve, along that curve. So in terms of that, if you look at one side of it and look at the weak formulation, because that is how we are defining a solution right now, we can go backwards, do everything in reverse, and get back to a smooth solution once more. What I'm saying is that a solution over here in the weak sense actually means it is a classical solution, but only in this region. Similarly for that side, they just don't agree along this path. So suppose this is the case we have. So this is the image. I took this from a textbook. Almost everything is from the same textbook. And suppose you are smooth and it is smooth on either side of this curve. And it is parameterized by some parameterization S of t comma t. There is this condition that comes. So suppose our function had distinct left and right limits at each point. That is what it means to be discontinuous. You approach from this side, you get a different answer. You approach from this side, you will get a different answer. For that UL and UR, and F is the original function which we had in the scalar conservation law. This condition must hold along every point of this discontinuity curve. This is a rather simple condition to derive. It just you integrate, you do some divergence theorem, and it just pops out. But it's tedious to do, so I just skip it. Here, S dot is the speed of the discontinuity curve. So let's show what happens for a particular example. So suppose this is the initial condition we are given. It looks like this. So if we do the characteristics for this, so what we do is we go here, it is +1, so it looks like this. These are the slope lines. This is, I'm doing it for the purpose equation. Over here we have it being non-constant. So when you try to work this out, they all do this. They all pass in the point 1, 1, this region, and then it is 0 from then on. So it's something like that. And they start intersecting after time 1. Till then, our characteristic gives us unique solutions. You pick any point here, there is only one characteristic, you can go back. You pick any point here, you go back. But here there is an ambiguity. You don't know which path to pick. So, what the Rankine-Huguenot condition, if you apply it and you solve for the path, assuming that there is some such discontinuity curve across which either side you have a smooth solution, you will get a path from here which says on this side you take it to be this, and this to be this. So by this I mean this is 1, any point over here is 1, every point over here is 0, and the 1 minus x is only on this small region. That is what the Rankine-Huguenot condition tells. It is a small calculation, but you have to do some work, you will get that. And this turns out to also satisfy the weak formulation which I had mentioned earlier. So what does this look like? If this is the initial condition, and you now start increasing the time, you evolve the system forward, it starts moving. Notice that this point is still fixed over there. This is still before time 1. You do this. And then at time 1, it becomes discontinuous. Notice we had started with a continuous function, and in finite time, it has become discontinuous. This is known as a shock wave. When the characteristics met, and this is a shock wave line. And it starts propagating after that. That is what happens. So it merges, becomes discontinuous, a shock wave is produced, moves forward. Sort of analogous to the body moving in air and all that. But this is just one space dimension and a much simpler equation. This is a different initial condition. This time I have flipped 1 and 0, and it is just 0 and 1 instead. I'm not trying this. You can do the similar characteristic thing which I had done earlier, and there is a small problem here. That when you draw those curves of discontinuity, which Rankine-Huguenot told you, you get multiple of them. You get infinitely many of them. 0 here, 1 here. This is the region where you don't know. It turns out that any line you choose seems to work, but you need to pick out one. These are all discontinuous solutions, but there still turns out to be a continuous solution in which you draw the characteristic emanating from 0. So the characteristics go like this, vertical, and they fall and they continue parallel. That turns out to look like this. So the wave sort of decays. That is what happens in this case. So I'll summarize quickly what we have done. So this problem is known as the Riemann's problem. Riemann was studying it whenever he was doing these sort of things. This was he did this for the general conservation law, and this is known as the Riemann problem, where you are given a piecewise constant initial function, and you want to know what happens. He solved it in its, I don't know if he did it, but someone did it. Someone solved it in the full generality, and they have given what happens. So if you start with the initial condition being UL greater than UR, then this is the only solution. This is again now shock wave propagation. You start with a discontinuous function, it just moves. You might notice I've written unique entropy solution. So I have not talked about what a uniqueness criteria means. I mentioned briefly that you will get multiple solutions over here. You need to pick out one which turns out to be the physically relevant. So in this case, it turns out to be a simple condition, but I have not mentioned it because deriving it and gaining intuition takes long for it. There is some condition, it doesn't have anything to do with entropy. It is just that people thought it doesn't decrease over time, let's just call it entropy. Something like that. And you do it for the other side as well. If UL is less than UR, you have a different set of solutions. So PD are hard to solve. We look at weak solutions. It is tough to find what the right conditions are to ensure uniqueness. What I haven't done is, once we have established that a weak solution exists, we can still try to look for smoothness of the solution. We can improve it, maybe prove that it is even differentiable, and we were just looking too broadly.
So for the penultimate talk of the series, we have Kumar Satudarshi from third year, and he will be talking on Brouwer 6.2.
For this project was Brouwer 6.0. I started from basics of topology. At the time I was not doing anything of topology. So the theorem is like this is ball in RL. This belongs to RL. And I'm defining one as x belongs to RL such that x square plus this is what the meaning of a subset of R, that is my ball, unit ball. Now I am defining a function which is continuous from ball Bn to ball Bn. Then the Brouwer 6.1 says that there exists a point, not only at least, there exists at least a point in this ball such that f of x is equal to this is my theorem. This is an overview of my theorem, what my theorem trying to say. So if I take any
what are you assuming about f?
Continuous.
Yes, sir.
Continuous. Because see, topology is more or less about continuity of functions. So this is like even if it's a map, it means it's continuous function. So this is what this theorem tries to say. If I take n is equal to one case, include one-dimensional case, then it's very easy to prove this. F of x is equal to x. Yes, let us suppose I'm taking example 0, 1 to 0, 1. This function is continuous. So, using intermediate value theorem, Bolzano's theorem, you can come up with a solution that directly a point such that f of x is equal to x. So, for one dimension, it's very easy to prove this theorem. But going to a higher dimension, this requires some stuff from topology. Not actually, you require some knowledge of topology. After that, you require some stuff from algebraic topology. So, let me first. Okay. I'm going to show you two proofs. Like these proofs are very easy. If you know some stuff, but I try to make those easy. First, I'm going to show some commentaries. And this is Spanner's lemma. It's lemma. Okay, so color chalk है क्या? Color chalk.
वो इससे पढ़िए.
I will write. Let's suppose I have a triangle. Spanner's lemma is generally for 8-dimensional simplex. But I'm just showing what it means in 2-dimensional case. So let's suppose I have a triangle and I am coloring its vertex with 3 different colors. Red, blue, and let's suppose this is yellow. Okay. Now I am just sub-triangulating this triangle. It means I am bringing other triangles inside this. This, yeah. So what triangle? What is trying to say? Yeah, you can do something else also. This is not correct. This. This is what I mean. So, what trying to say? Let's suppose this is red, blue. This is yellow. So all of these vertices you have to color with the color that is not yellow. It means I can only color this with blue or red. I can color this with any color with blue or red. Similarly for this, I can't color these two vertices with red. I have to only color with blue or yellow. Similarly, I have to color these two with any other. Okay, don't think about the colors, but you can randomly. And then you can also color this with any random thing. It's not necessary that you have to color anything as special. Inside thing you can do it with any color. But on the edges, this is fixed, like you have to do the coloring with the vertices, which is not same as the opposite, like this side's opposite vertex. So this is trying to say that there exists a triangle inside this triangle, in sub-triangle, which has all different vertices, different colors. All different vertices are different colors. This is what Spanner's lemma trying to say. And this is for 2-dimensional cases. Going to 3, 4, n dimensional, you have n dimensional and simplexes. And in the n simplexes, you will also come across this type of lemma. Proving this lemma requires induction and some other stuffs. I'm not going to give any proof, but I will touch any video where you have any proof of this thing. So now what I'm going to do, I'm choosing a point outside and I'm trying to travel inside this triangle such that I can only cross a side if its two vertices are of same color. Okay? Let's suppose this is blue, this is red, this is also red. So I can only pass through this. Okay. After this, let's suppose
those two vertices aren't allowed to be red, no?
Wait. Blue. No, this one blue. No?
Yeah, but red are not allowed.
Oh, sorry. So I can only do yellow, yeah, blue. Something like this, fine. So, like, what happens if I go with this red? You can also see. So, if I'm going to travel through this particular triangle, if I enter into this triangle, I have no point to go outside because all of them has all different. I can enter in this and this, but if I even cannot enter in this because there are no two vertices of same color. So this triangle has some notion of fixing. I'm not telling this is fixed point proving it, but this triangle has some notion of fixing. Like in a triangle, whole triangle which has different colors in their vertices, I have a triangle which has all the vertices same color. So now I should not use this word, I'm using similarity. What I'm going to say is that this triangle is similar to this triangle. With respect to that, their colors are different. You can find there are more than one triangle of this property. Inside this also you can triangulate it. Okay? You can also triangulate it. After it also you will find, because Spanner's lemma, there are sub-triangle which are all the vertices are different colors. Doing again and again, you will find that you will just go, this will end up to point. If I do this infinite number of times, this is just bounding inside a triangle, then again a triangle, then again a triangle. So this is a thought of proving a fixed point theorem by using Spanner's lemma, by the thought of going through a path. And अंदर आके फंस गया ऐसा समझता है ना, तो this is like that way only. It will be like from this particular triangle there is no other way to go outside or inside. So this triangle is what fixing us, and it
iteratively doing it infinite number of times, we will have a point which is like, this is some notion of fixed point, but to prove this theorem, to use this lemma to prove requires something else, but this is a big overview of what we are going to do to prove that fixed point thing, because we know contraction principle. Whatever contraction principle we know. So we know contraction principle and we know that distance between any 2 points is always as C multiplied by distance between x and y. These two distances function can be different. But we know this contraction principle. Contraction principle assures at least not if and only one fixed point inside a closed set. So this contraction principle we are getting because we are just contracting our triangle inside each other. So this is one of the way we are trying to prove the fixed point. There is another way that this is the part which uses the combinatorial way to prove fixed point. And do you know about this? You can find this lemma on YouTube and you can find more stuff on this. To prove through topology, you need something called fundamental groups. So, if there are two spaces x and y which are homomorphic to each other, x is homomorphic to I'm using this. So, if x is homomorphic to y, so their fundamental groups are also same. Means homomorphic, isomorphic, not same, isomorphic. The fundamental groups are isomorphic. So, if I can find a continuous function f from x to y, which contracts this space to y, which suppose x is here, I have a function which contracts this to y, then their fundamental groups will be also same. Contraction is one of the way where we like, let me say what I mean by contraction here. Let's suppose this is I have a disk. Because I proved this lemma in 2 dimensions, let's suppose I have a disk. Okay? And what I am trying to do, let's suppose I have given a function. So this one a disk, close this to its boundary, okay, S2, S1. So I am defining a function from D to S1 such that given a function G which is continuous, so let us suppose there is a point X inside this. Corresponding to this point X, I find a G of X here. Okay? So I have two distinct points. After that, what I am going to do, I am going to draw a line from here to here. Okay? And direction should be this. There is importance of why we are choosing this direction. So direction should be this. So what we are doing, we are projecting this G of X onto circle, such that where we are projecting here. Means given is here, a function continuous from D to D. Okay? So now if I am given a point X, I find a G of X which is also lying in the D. So I am just connecting these 2 points, and these 2 points are going to meet on a circle somewhere because I am drawing this indefinitely in one direction. So I am just projecting this point to here. If I am able to, if there is no fixed point, okay, if there is no fixed point, I have a way so that I can contract the whole this minus S1 is inside, because if there is a point this, which if there is a point, let's suppose x prime, and this is gx prime, so this is fixed because means the projection of this point is fixed because you are just projecting x prime on x prime on. So I'm not concerned about the points on the circle. I just point inside the disk. This what I'm trying to say. If there is a point inside such that there is a if there is something, we have always a line which can project. Okay, so this particular function is fixing outside circle, but it is contracting the whole disk into the circle. Means I should not. The word is contracting. It's not intuitive. It should be like we are projecting this disk on the circle. So this is a way. This particular way. This is a way to contract the whole disk onto the circle. So if there is no fixed point, what will happen? If there is no fixed point, I can contract the whole disk inside on the circle, because if there is a point x, so that g of x is there, we cannot define a line. Simply we cannot define a line. So we cannot project this point on any of the point on the circle. So if we are able to, if there is not something like this, if there is not something like fixed point, we can contract the whole circle, whole disk inside this on a circle. That means the fundamental group of the boundary, that is D minus S1, I should say this is S1, is equivalent to what? This should be same. This should be same if we are able to contract this. But fundamental group of this is, I guess that, but this should be that, and this is trivial. If fundamental group is trivial, it consists of only one point. I will once again I will tell what is fundamental group, but this is not homomorphic to one single point. So this is contradiction. So because we cannot do this particle contraction, this ensures that there exists at least one point where we cannot do this type of stuff. So that's why we have something called fixed point in 2 dimensions. To go to another dimension, 3, 4, because this is a proof that is useful for only 2 dimensions. Because when you go for higher dimension, you can say, okay, we can do this for sphere also. Take a sphere, there is a S2 and there is a ball, V2 minus V2. There is a ball is here, I can put it ball. We can also do the same thing. We can take a point, project it on the surface, and what is going to happen. The things that comes out is, like if we take V2, I should take V2, I'm not recognize this. It is a ball in the 3 dimensions, so S2. This is homomorphic to S2 only. V3, quotient of S2 is homomorphic to S2 only. Means the fundamental group, the fundamental group of this is homomorphic. So this term we can't use in 3 and 4 higher dimensional cases. There we use something called homology. For that we require something called homology and simplicium homological. Things that are good stuff to go again, but fine. So this is the fundamental group concept that we are using here. And cohomology is what we will use. We use for higher dimensions. But Sperner's lemma on the other side uses simple Sperner's lemma stuff to prove the theorem for all the dimensions. But the point is Sperner's lemma something new? Means is there something new than fundamental groups? Because for understanding this group, you should know what is fundamental group. You should know what is homotopy. You should know something about what algebraic topology is for, and then something for large part of topology. But Sperner's lemma is simple combinatorial stuff to prove the fixed point theorem. The question is there something new in Sperner's lemma? The answer is no. Sperner's lemma is similar and same thing with this, but the point is, inside Sperner's lemma, when you prove Sperner's lemma, you require something from topology itself. So proving the Sperner's lemma requires something there, because not something for topology is intrinsic to something from topology. So fundamental group stuff is one way to prove this fixed point theorem, and then Sperner's lemma is another. So what is its use? Like what are its uses like? Why do we care about fixed points? So fixed points we use for solving PDs, ODs, and also fixed points are very useful in game theory, because proving the Nash equilibrium requires this Barabar's fixed point theorem only. If you are going to prove that, is there any way for in a two-player games that we have a Nash equilibrium stuff, we require a fixed point theorem. So the use of Barabar's fixed point theorems comes there. And also, suppose there is no, for one dimension also you can think of these stuffs by plotting any graph, like if I have 0, 1, I can plot any graph between 0 and 1, and I can also plot y is equal to x. I have, suppose this has 3 points, it can have 2 points. So, thinking in one dimensional case, it is very easy to come up with this particle. But in 2, 3, 4, 5 dimensions, why there is something like this? So, to understand that, like, what is the motivation behind to think of a fixed point theorem? These all motivations come from PDs and ODs, because we need something there. And also for inverse function theorem, we need fixed point. There are many fixed point theorems. This is one of the fixed point theorems, it's called Brouwer's fixed point theorem. And again, it has Sood's fixed point theorem, Tarski's fixed point theorems, and Banach's fixed point theorem. So all those fixed point theorems are something like this. One thing that is very that is different from others, not from different from others, the contraction principle point is, this is not a constructive proof. We are not constructing any fixed point here. We are just giving an existence of the fixed point. But for the contraction principle, we have a sequential criteria in which plotting a sequence, we can find a fixed point. Yeah, sequential criteria, the contraction principle gives us that there is at least only one fixed point, but here it can have more than one fixed point, like in this case. So there is also use of this in a dynamical system stuff, because for fixed points you need dynamical system where the system is going to halt. Then sometimes I forget that in the class, but if system is there, like so in the spinner schema only, you see that inside a triangle we are going, when we found one triangle which have all the same property in the outer part, we are going inside and going to halt at a point. That is called an equivalent point here. In the dynamical system, there is another way. To understand dynamical systems also, either it means we are not a complex dynamical system. We are simple dynamical systems. There is something. So to understand simple dynamical systems, we require what is called fixed point theorems. Okay, so let me finish. This is all about this fixed point theorem stuffs. What are the other thing that I did in the summer with the topology stuff is something called topological insulators and something called Dirac point. So you have heard of graphene. Graphene is two-dimensional materials in which we are like there are many research going on say graphene. So what happens? You must have heard of band theory of metal. Band theory of metal. This is conduction band and this is valence band. If both overlaps, this is becoming conductor. If there is a large gap, this is insulator. And if there is a lesser gap, means there is overlap, but there is a lesser gap, then it is semiconductor. Now comes something called semi-metal. What is semi-metal? Semi-metal is like continuously deforming both bands. That's why we use topology there, such that we have something like this. This is my valence band, this is my conduction band, and this is called Dirac point. And this is why we have something called topological insulator. What is topological insulator? I have a material whose bulk is insulator, but whose surface is conductor. Like it can conduct through surface because this particle Dirac point is present only on the surface, not inside the bulk. So this is a point because this is semi-metal because there is one point. So electron can also go from valence band to conductor band. So this also requires some stuff from topology. This is fine. Beyond.
Thank you. This is the final talk of the series. So we have Aviral Sood, third year, and he will be talking on optimizing intersections of convex polygons under rigid motions.
So that's the title of what I did. My presentation is very simple. It's just an introduction to the topic of computational geometry. And if all of you can cover it quickly, then I can tell about one or two more exciting things. So to the first years here, no big O notation, big O of n.
Somewhat computer classes you have.
Yeah, so just big O of n, like in general you can say it's
less than c times g of n.
yeah. So it's approximately it takes n steps. So big O of n means that it takes somewhere between c1 of n and c2 of n steps. That's the number of steps it's taken. C1 and c2 are some constants. So big O of n again, big O of n square. It just shows like how many steps you're taking up to some linearity. So that's the only thing I'll be assuming as this turns out. So why should we care about computational geometry? Because it's computational geometry is just part of discrete mathematics where we are applying algorithms to some geometrical problems. So it's important because if you ever played like 8-ball on your phone or Angry Birds, so that's collision detection between two objects. That's a part of computational geometry. You have to plan the motion of a robot, which is a 2D object, around a maze, which is another 2D object. That's a part of computational geometry. You have to make meshes of objects and just stuff like that. That comes under this. So one important concept in computational geometry is convexity. So any convex set or any convex figure is a figure in which take any 2 points within the figure and you can connect them within a straight line, and that straight line will lie within the figure. So I have these 2 points x and y, I can connect them with a line and I have no problem, it's all of it is within the figure. And this is not a convex set because this line goes outside the figure. For polygons it has a better definition because a convex polygon, all the interior angles will be less than 180 degrees. But for a concave polygon, you can see that even if one angle is more than 180, which is called a reflex angle, then a straight line will pass outside the polygon. It will not be convex anymore. And convex sets are very important for optimization problems. They have very nice mathematical properties. And they're also useful for things like collision detection. So, like, say you have a set of n random points, like, say you have two cars, and you have like these points which are on those cars, which are tracking, you can't track the whole car, and you want to find the collision between the cars. Like, say these objects are very complicated. So, in general, collision detection between two figures is computationally it's expensive. So, one shortcut you can take is find the smallest convex set which contains all these points, and find the collision between those two convex sets, which you can do much more efficiently. And then you can define it and then find out if there's any actual collision happening. So that's where this concept of the convex hull comes in. The convex hull is the smallest convex figure which contains any given set of points in the plane. So for a given set of points, like you can have a convex hull of two circles, two lines, and whatever. I'll just take a set of points to be simple. For a set of points, the convex hull is always a polygon. You can prove that, but I will not be proving that here. So if all these three are the same sort of points. So this is a set containing the points, but it's not convex. This is a convex set, but this is the smallest convex set which contains all of these points. So this is a very important problem, like how we can calculate that efficiently. So one very naive way to do that is by just use induction. Like I know I can solve it for k points, I will solve it for k plus 1 points. Just I have this set of k points I know it's convex hull, and I have to just join it with this new point p. How can we do that in a reasonable amount of time? Because we know that the convex hull is going to be a polygon. So I just have this given convex hull, I have this new point P. I draw lines from P to all of these vertices. This new convex polygon I will get, it will contain this polygon obviously, but it will contain some of these straight lines that will bound it because it's again a polygon. And there will be one line which makes the largest angle in the clockwise direction, which is this upper line. And there will be another line which will make the largest angle in the lower direction, which is this lower line. Both of these are called tangents. So this has the largest angle clockwise, this has the largest angle anti-clockwise. And all the lines in the middle, they just get included in the final convex hull and we remove them. So for any point, you can take a point anywhere, you always get two tangent lines. And with that you can construct a new convex hull. And to do that you have to draw lines to all the boundary points. So I will just time analysis of how long it takes. So at the kth step, when we have k points here, and we have to add 1 point to the hull, we have to check for all the points on this, all the boundary points I have to check. And there can be at most k boundary points. Like I did some insight, but there are at most k boundary points. So at the kth step, we are doing OK actions. And we just add up all of this and we get that the whole algorithm is O(n) squared. So the very naive implementation gives us O(n) squared time. But can we do better? So this is Ron Graham. In 1972, he published the first paper on computational geometry, in which he gave an O(n) log n algorithm for the convex hull. Like he was working at Bell Laboratories and he wanted to find the convex hull of a 10,000 point set, and the computers of that time could not handle that. So created a new algorithm to take care of that. That was called the Graham-Scan algorithm. So I'll describe the steps of it first and then I'll show an example later to clear things up. So the first step, given just a set of points, we will choose the bottommost point. And I assume that there's a single bottommost point because the chances of multiple bottommost points occurring are close to 0 and we can get rid of this spaces easily. So that takes O(n) time. I just go through all the points, I take the one which is has the smallest y value. And then I sort the remaining points in S. In increasing order of the angle, they make the horizontal. That means I have this set of points. I have this bottommost point which is my angle, and I look at all of these lines. So this is my origin, and I draw lines to all of these points. And this makes the largest angle. So this is my first point. This is my first point. So this will be my second point. This will be my third point, fourth point. So I just order them by their angle. And that ordering it's a sorting. So a sorting takes O n log n time. So that's a standard fact in computer science. And we move along the sorted points in order, and we remove a point if the angle it makes with the ones before and after it, it's a reflex angle. So I'll just go through an example and show how it works. So I have this random set of points at first. I have the anchor point, and I have ordered them according to their angles. Now I add 2 to it, to the potential boundary. I add to the potential boundary of the convex cell. Then I add 3 to it, and there's no problem because 1, 2, 3 is not reflex. And then I add 4 to it, there's again no problem. 2, 3, 4 is a convex again. But once I add 5, then 3, 4, 5 is reflex. So I have to remove 4. And then I go back to 3, and again 2, 3, 5 is reflex. So again I remove 3. And now 1, 2, 5 is not reflex, and we are fine. And we just carry on like this. We add 6, there's no problem, but once we add 7, we have to remove 6. And then finally from 7, we can just directly go to 1. And this gives us a complete convex set of the convex cell of the set of points. And the initial sorting, it takes the 1 log n time. This is the most expensive part of the process. And during a scan, like each vertex, so say vertex 3 in this case, first it's considered when it is added to the list, and the next time it's considered, if it's considered at all, is when we are removing it, and then we don't touch it again. So each vertex is visited at most twice. So the scanning part, it takes on time. So that's the easy part. It gives on log n time overall. So this is much faster than the naive algorithm. The only problem is we are dealing with the angles. There are multiple ways to deal with angles computationally. You can use dot products, you can compare dot products. But if we have like a lot of points, then we need a lot of precision to figure out, oh, this point is before this point. Like your precision may run out before you can do some sort of meaningful progress. So there's another approach to it, which takes the same one log n time, which is the divide and conquer approach. So if any of you guys know like merge sort, which is a method of sorting in computer science, this is basically like that, but for convex cells. So again, it's a type of induction. We just assume we can do it for all smaller sets, and then we order those sets by their x values. So now instead of picking an anchor point, I have this set of points I have, and I order them by the x values. So this is 1, this is 2, this is 3. So left to right I order them, and then I just divide into 2. So n by 2 points I have here, and n by 2 points I have here. So it can be more than 1, less than 1, like there can be difference of at most 1 between them. But I have divided them into 2 groups. And I calculate the points of this in some time, and I know I can do that. That is the assumption by induction. And the tricky part is we have to join these 2 convex cells into a bigger convex cell of the whole set. And that, if I do efficiently, then the whole thing can be done in a pretty efficient O(n) log n time. So this is quite similar to the incremental approach, and I'll not go into the details too much. The thing is basically I have this set A, I have this set B, and their union, the union of the convex cells, it again looks like this. They are again 2 tangent lines always. And when we pick these 2 tangent lines, then we remove all these lines in between, and we get a bigger convex cell. And these tangent lines we can find in O(n) time. So you can think of it like we have to find the upper and lower tangent lines separately, and that we can do by just starting from the farthest point with the x coordinate farthest to the right, and the one with the x coordinate farthest to the left, and then we just walk up the stairs up the polygons. So we are here, and then we can move up here because it's visible. Then we can move up here because this is visible, and then we can move up here because this is visible. And then we stop because there's no more visibility. So just walking up there, it takes O(n) steps, and we can calculate the 2 tangent lines this way, and so we can join these 2 together in O(n) time. So this is just like merge sort. We have 2 this, and we which are sorted separately, and we can join them in O(n) time, and and the whole thing takes a long time. I'll not do the time complexity. So this is a nice problem if you want to try it. That it is true that you can't go below O n log n. That's the optimal time complexity. And this can be proven, but I will not ask you to prove that. You can try proving that if you are given a polygon, which is can be convex or concave or any other shape, then we can find a convex hull in O n time. So that is possible. If you want to take a look at that. Now I will cover the third type of common use algorithms in computational geometry. So triangulations are basically like if you can divide every polygon into a union of triangles which are disjoint and which cover the entire polygon. So this is an example. And it is known that every simple polygon, be it convex, concave, it can be triangulated. Now the question is how we can find this triangulation for any polygon efficiently. For convex polygon, it's not really a challenge because for convex polygons, I can again do this sort of thing. I just sort of convex polygon. I just go from left to right. This is already a side, so I can't join it. But then I have this point. This is my first point, second point, third point by the x coordinate. I just join 2 to 3, and there's nothing stopping from doing that because this is a straight line. It will be contained in the polygon. And then look for the next one. 3 I can't join to 4, so I join it to this thing, and then I join it here. And now successfully I have triangulated the convex polygon. So using this, we develop a sort of algorithm that moves from left to right. And it's a very commonly used technique. It's called a plane sweep algorithm. So in a plane, given a set of points, if you want to make a Born diagram or anything that's commonly used in computational geometry, you use plane sweep algorithms. You order the points from left to right, and you construct a triangulation piecewise. Like at any given point, say the line is stopped here, this triangulation is complete and this is incomplete. So you just build it iteratively as you go along those points. And the time complexity for the whole triangulation is O n log n, which is quite reasonable. It's not the fastest algorithm, but this is the most commonly used. So we generalize this notion of moving left to right and triangulating for monotone polygons. And monotone polygons are basically like I have a more rigorous definition, but basically they are polygons where the vertical line only intersects them twice. So there can be polygons like something like this, and the vertical line here intersects it in 4 points. So this is not monotone. So you can think of it like if I take the farthest 2 points, it gives me 2 like chains which move from left to right. That's a monotone polygon. So it intersects the upper chain once and the lower chain once. And it can be proven like quite easily that monotone polygons can be like triangulated in a similar way, just by moving to left to right. It's slightly more complicated than the convex case. We are just proving for a simpler case, then I will prove for the general case later. So I will divide the general polygon into monotone polygons, and I will triangulate each of them, and I will join it together to get a general triangulation. So we can do this in O n time, and this is just an example. If you want to get into it like really well, I can link I have linked that reference at the end. But basically, you move along here, and all the convex lines you join easily. But here you get like reflex angles. So the 4, 5, 6, you don't join them because they will be outside of the polygon. You wait until you hit this 7, and 7 is can see 4, 5, and 6. So you join them immediately. And then again you can just join 6 and 8, but then you have these 3 points 9, 10, 11, can't join them immediately. So you wait until you hit 12, from 12 you can get to 10, and then from 13 you can get to all of them. So it's just iterative. It's slightly complicated, but it is pretty intuitive. Now for the gender triangulation algorithm, we'll look at cases like when can a polygon not be monotone. When does this not coincide right? So this polygon, it has this sort of edge where 2 lines are meeting and then merging together. So this I'll call a merge vertex. here you can see. So the interior is this, and the two lines are meeting, and this forms the merge vertex. Because just to the left of the merge vertex, it will intersect in at least 4 points. That contradicts the monotonicity. And there's another type. It's a split vertex. So it's just a mirror image of this. Just look at something like this. So this is my polygon, and this is my sweep line, and this will be a split vertex because it's separating the inside into 2 parts. This is not what I want. So how I get rid of them is I do another plane sweep. So this is my general. It's a very weird looking polygon. I just do a sweep. So I just order the points left to right, and I've drawn vertical lines at each of the vertices. That's all I've done. So to remove those split vertices, so I have this is my split vertex, this is the merge vertex. I will take care of all of these. I have to remove all of them. So what I do is for each split vertex, I join it to the vertex just to the left of it, and for each merge vertex, I join it to the vertex immediately right of it. And I can draw these lines because they are adjacent in the x coordinates, so they won't go outside the polygon. And this it will divide the polygon. So I draw all these lines. For each split vertex, I will join it to the left. For each merge vertex, I will join it to the right. And then I get all these subdivisions, and none of these subdivisions will contain either a merge vertex or a split vertex, because both of them I have eliminated. Because in this section, so this was a split vertex, it was going to the right, but I have joined it to the left. And now, so there is no contradiction of monotonicity. So I have all these pieces, each of which is monotone. And then I can do another round of plane sweep, and I can triangulate each of them one by one. And I can join all these triangulation, and I get a general triangulation of this whole polygon. So again, this sweeping part is ON, and the sorting part is ON log n. Yeah. So that's the end of the topic. So there's a faster algorithm possible. There's a ON algorithm for triangulation, but that is so complicated that no one will ever use it ever in a computer system. So these types of ON log n problems are mostly used. So yeah. So these are my references, and
so yeah, that brings us to the end of the seminar series. I'd like to thank all the speakers who gave talks on this series, and to all the people who showed up. Yeah, thank you.
Thank you. And thanks to the juniors who stuck through all those difficult presentations.
Yes.